We can view the Sun, planets and stars from Earth at very vast distances. The Sun is the closest star to us, and it is 150 million kilometers, 93 million miles away. Distances in space are too large for kilometers and miles to be accurate, yet they work well for measuring distances on the Earth's surface. Light and other types of radiation that travel at approximately 300,000 kilometers per second convey a wealth of information from space. The light from the Sun takes approximately 8 minutes and 20 seconds to reach Earth. We can see the Sun as it was 8 minutes and 20 seconds ago. We say that the Sun is 500 light seconds away. Light travel time refers to the time it takes light to reach a distant location. When discussing a distant body, light travel time is a convenient approach to measuring large distances, as it immediately informs us how far back in time we are looking. We still see a star that is 10 light-years away, about 100 trillion miles, just like we did 10 years ago. When we stare out into space, we inevitably look back in time. It takes light around 10 hours to travel from Pluto's orbit to the Sun, which is the distance across the solar system. Our planetary system, which is enormous by Earth standards, appears small because the nearest stars are located several light-years away. There are billions of stars in a vast area that stretches for tens of thousands of light-years. They are the stars that shine the most in our galaxy. There are other galaxies out there, millions of light-years away from us. Most of these galaxies are massive groups of stars, with billions of stars. The universe is so vast that even astronomers, accustomed to thinking about enormous distances, are amazed. Time has been used sparingly, so who would be startled by only a few thousand, a few million, or even a few billion years of light travel time? However, the odd units of measurement we employ on Earth make this space seem so vast, and this time, it appears so brief. We set aside our preference for measuring distances in small and large units, and used the time it took light to travel to measure distances. A lot, but 1 second of light travel time is equivalent to 300,000 kilometers. The most extended distances on Earth are only 1/20th of a light second long. We live for 70 years. During that time, the Sun and its planets only move about 20 light-years in the galaxy. We live in a small space in the universe, but we last a long time. This information helps us explain why people are more interested in the extent of space than in its duration over time. The first method exploits the parallax effect on stars that are barely a few hundred light-years away from Earth. We can notice the parallax effect extremely clearly when we hold a finger straight out in front of us and gaze at it with both eyes. The finger appears to be moving back and forth. The stars that are close to us are also in different directions, depending on where we are in our orbit around the Sun. When you look at a star from 2 points in the Earth's orbit that are 1 astronomical unit apart, you see it in different directions, separated by an angle of 1 second of arc. When you look at a candle flame from 10 miles, 16 kilometers, away, you see it with your left and right eyes at different angles, separated by 1 second of arc. Observing stellar parallax becomes increasingly complex when the distance exceeds 300 light-years. If the stars are too far away for their parallax to be noticed, the second method can be used. We pick these faraway stars because they are very much like stars that are closer to us. You can tell how far away stars are by how bright they look and how far away they are from other stars. Every star has an intrinsic or absolute brightness, and its apparent brightness changes depending on how far away it is from Earth. For example, we can tell that a star is 100 light-years away by using parallax measurements. A second star is seen that looks less bright, but is thought to have the same brightness as the first star. We learn that the second star is about 1 1/100th as brilliant as the first one. If there is no absorption between stars, the star gets dimmer as the distance increases. This suggests that the dimmer star is 1,000 light-years away. Let's go to space and see all the different stars. A few stars are incredibly bright, but most are not as luminous as the Sun. We can also observe that most stars are part of groups consisting of 2, 3, or more stars. There are many binary systems, sometimes referred to as double stars. Approximately half of the stars visible to us are in binary systems. Most of the time, double stars are separated by astronomical units and move around each other for years at a time. But other double stars are much closer together and only last for a few days. They trade things, have violent outbursts, and change in ways that are both astounding. Without binary systems, the average distance between stars that are close to each other is about 1 parsec. This distance is approximately 200 trillion astronomical units, equivalent to 20 million times the diameter of the Sun. The distances between stars are enormous, relative to how large the stars and their solar systems are. Light and color. What are the stars? They are glowing balls of hot gas that discharge radiation into space and are held together by gravity. The first things that come to mind when you look at them are their color and brightness. The brightness of a star depends on how much light it sends off, and the color of a star depends on how hot its surface is. The HR diagram, also known as the Hertzsprung-Russell diagram, illustrates the relationship between a star's luminosity and its spectral type. Each point on the HR diagram has a certain balance of hue and brightness. The Sun is a yellow-white star that is 5,800 Kelvin hot on its surface. Many more stars are yellow-white and are around the same size and brightness as the Sun. Red giants are large. Red stars characterized by their distinctive red color. Their surfaces are quite heated, roughly 3,000 Kelvin. Some of them are pretty little and white, and their surfaces are at least 10,000 Kelvin hot. The brightness of a star, or how quickly it gives forth light, depends on how hot and big its surface is. A red giant star is very brilliant, even though its surface temperature is low, because it has a lot of surface area. A white dwarf with a high surface temperature doesn't shine particularly brightly, because it has a little surface area. A red giant star is like a charcoal fire in that it is very hot and gives forth a lot of light. On the other hand, a white dwarf is quite dense. Even when some of it isn't visible, we typically want to know how much radiation a star puts off. Radiation refers to all types of radiation, including both visible and invisible forms. The most common method for referring to a star's brightness is in terms of its solar luminosity. When we put each star on the HR diagram as a point, we can see that the points don't just spread out randomly. They tend to cluster in certain places. The main sequence is a diagonal strip on the figure that contains most stars, including the Sun. Stars that are red, cold and low temperature, in the main sequence don't shine very brightly, whereas stars that are blue, hot and high temperature do. All main sequence stars stay bright and gain their energy by converting hydrogen into helium through nuclear reactions. As you go along the main sequence, the stars get heavier. The smaller stars at the bottom of the main sequence transform hydrogen into helium over time, while the massive stars at the top do so quickly. The Sun is around 1/10 to 10 times as big as most stars. Their surface temperatures range from 2,500 to 25,000 Kelvin, and their brightness ranges from 1/1000th to 10,000 times as luminous as the Sun. Stars in the main sequence have a wide range of brightness levels. The brightest star has a radius that is around 25 times that of the dimmest star. This means that their diameters are not significantly different from each other. Many stars are less than 1/10 the mass of the Sun. Red dwarfs and brown dwarfs are faint stars that are often hidden partners of visible stars. Some massive stars are 10 million times brighter than the Sun and 60 times their mass. A star that is as bright as Alpha Centauri would light up the Earth as much as the full moon does. They are no longer on the main sequence, having exhausted their hydrogen supply. As they hunt for more energy sources, their centers are getting smaller, hotter, and denser. On the HR diagram, white dwarf stars are below the main sequence. White dwarfs are nearly the same size as the Earth. They are thick, heated, and not very bright because they have a lot of surface area. These stars have finished changing and are slowly getting colder. There are a lot of these dying stars. About 10% of the stars surrounding us are white dwarfs, but they are hard to find since they don't glow very brightly. Not every star dies as a dense white dwarf. Some of them turn into neutron stars, and as we will see later, some become black holes. Most stars shine all the time, but some, called variable stars, alter how brilliant they are from time to time. About 25% of all variable stars are binary systems that eclipse each other. The stars that orbit them pass in front of each other often, which makes them look brighter. However, most of them are pulsating variables that regularly change in size and brightness. A collection of bright yellow giants above the main sequence is a type of pulsating variable. These stars are known as Cepheids. They are called thus because the first star detected in this group was Delta Cephei, a faint star in the constellation of Cepheus that you can see with the naked eye. They shine between 100 and 10,000 times as luminous as the Sun. Our galaxy has more than 700 Cepheids. Most of them pulse every 3 to 50 days, and some can get up to 5 times brighter. Polaris, the pole star, is a Cepheid variable that increases in brightness by 10% every 4 days. Cepheids are stars that are larger than the Sun and were once red giants. Oscillation helps Cepheids release the radiation they've stored. We need Cepheids because they help us determine the distance to other objects. We know that the periods of their oscillation are linked to their brightness. The brighter they are, the longer their periods of oscillation. In 1912, Henrietta Leavitt, an astronomer at the Harvard College Observatory, discovered this link between brightness and period. An astronomer can tell how bright a Cepheid is by looking at how long it takes for its brightness to shift. They can then determine its distance by comparing its apparent brightness from Earth with its actual brightness. When it comes to deciding distances, astronomy can be a complex field. But this interesting method shows why the comparatively rare Cepheids are so significant. Stars are balls of gas that are very hot and send energy into space. This energy originates from deep beneath the Earth and slowly rises to the surface. The center of a star is substantially hotter than its surface because heat transfers from hot to cool places. The centers of stars are incredibly hot. The Sun's core temperature, for example, is roughly 15 million Kelvin. As stars move from low mass to high mass stars in the main sequence, the temperatures in their cores climb. Self-gravitation keeps stars together. A force pushing outward pushes against the gravitational force pulling inward. The hot gas inside the system pushes everything out because of the pressure it creates. If there were no pressure in the Sun, it would collapse into a black hole in an hour. It's easy to see how gravity and pressure work together to maintain balance. Imagine that the shell of a star is made up of two circular surfaces that are next to each other. The pressure on the outside pushes in, while the pressure on the inside pushes out. This is the equation that describes a star's hydrostatic state. The star is made up of a lot of imagined concentric shells. The pressure goes up every time we cross one. The pressure continues to rise until it reaches its maximum peak in the middle. The cores of stars experience tremendous pressure. For instance, the pressure at the center of the Sun is equivalent to having 100 million tons of weight on Earth, but only across a space the size of a dime. Why is the temperature so high? The Sun's average density is 1.4 grams per cubic centimeter, which is 1.4 times the density of water. The density in its center is roughly 150 grams per cubic centimeter. The crushing pressure inside the Sun is too much for any of the usual states of matter, such as solids and liquids. In these conditions, the only thing that can exist is a gas that is hot and thick. We are not aware of any other gas that is as hot as millions of degrees. Atoms move incredibly quickly, hundreds of kilometers per second, and when they hit one another a lot, they lose their electron clouds. So, most atoms are ionized, which indicates that they have lost all of their electrons. The gas is composed of negatively charged electrons and positively charged atomic nuclei that can move independently of each other. The radiation in this hot, thick gas isn't the soft, beneficial light that emerges from the colder surface. It is intense X-rays, not something else. The deep interior has a lot of radiation that goes about 1/10,000th of a centimeter on average before gas particles catch it or bend it. The density times the temperature is what makes the pressure in this kind of gas. The centers of stars are very hot because of the enormous pressures that keep them from falling apart due to their gravity. So, we now know what makes stars sparkle. The insides of these items get hot because they have to bear a lot of strain from gravity. The radiation in the hot gas slowly moves to the surface and then into space. Nuclear reactions release the energy that was lost, which keeps the stars burning for an extended period. Stars don't shine because of nuclear energy. They shine because their huge masses generate a tremendous amount of internal pressure. Gas particles inside a star constantly scatter the radiation, which makes it considerably more challenging for the radiation to reach the surface. Radiation takes approximately 20 million years to travel from the center of the Sun to its surface. If nuclear energy suddenly stopped being created in the middle of the Sun, we wouldn't know anything was wrong for 20 million years. Sound waves and convection. Opacity refers to the degree of resistance that radiation encounters as it flows. As the opacity increases, the gas often absorbs radiation from the inside, and convection transports the energy. Gas gets mixed up, and currents that rise and fall move heat energy to the surface. The Sun's outer layers, or envelope, are very thick, so radiation can't easily reach the surface by diffusion. This mechanism causes the Sun's envelope to move like water in a boiling kettle, which sends heat to the surface. Stars that are smaller than the Sun have convective envelopes that are deeper. Stars that are more than twice as big as the Sun don't have convective envelopes. Instead, they have convective cores. In bigger stars, nuclear energy comes out of a small area in the middle. The core then starts to convect, because radiation can't transfer energy through it quickly enough. The song of a star is the same as the song of a whale. Inside the star, some sounds range from deep, rumbling noises to high-pitched screams that make you shiver. No one has told a star how big and round it has to be, how bright and hot it has to be, or how to keep getting the energy it sheds off its surface. Sound waves can get through a star like the Sun in about an hour. The star is always attempting to restore its original balance by making subtle adjustments and sending sound waves to all its sections. The star always moans and heaves at the lowest vibration levels. At the highest modes, which are 60 octaves higher, it is filled with the sound of particles moving quickly and colliding with each other constantly. The study of the vibrations on the Sun's surface is called helioseismology. It provides us with a great deal of knowledge about the Sun's inner structure. The Sun is like a prominent speaker. The material becomes less dense as it moves from the center to the surface. Like a whip, each sound wave becomes larger as it moves away from the source. A strong torrent of sound hits the surface, runs through it, and then fades away in the thin outer atmosphere. When the Sun's convective envelope is noisy, it gives off sound waves that heat the corona, which is the Sun's uppermost atmosphere, to 1 million degrees Kelvin or more. Because the corona is so thin, it can't bounce back the energy it gets. It can't do anything else, so it just expands and carries the energy with it. The corona is like a big jet engine. It takes gas from the Sun and sends it out at high speed after heating it with sound waves. The solar wind is what gives off this energy. It travels outward and sweeps away approximately 100 billion kilograms of gas every second at speeds of several hundred kilometers per second. There are also stellar winds from other stars that come from the noise inside them. These stellar winds can be more substantial than the solar wind at times. Some stars even explode after millions of years. Stars are huge nuclear reactors that make energy by breaking down atoms. Nuclear activity deep inside the Sun makes the sunlight that strikes the Earth's surface. We shall take a break to understand how stars create energy at the atomic level. Atoms join together to form molecules. Atoms can share or trade their outermost electrons. This produces electrical forces that hold the molecules together. Atoms make chemical energy when they come together to make molecules or move about. Most of the energy people use comes from burning fossil fuels, such as wood, coal, oil, and natural gas. Each atom has a small, positively charged nucleus at its center. This nucleus is surrounded by a cloud of negative electrons that is much greater. The nucleus is made up of nucleons, which are either protons or neutrons. Neutrons and protons have the same mass. However, neutrons don't have a charge. Protons do have a charge. Strong nuclear forces hold together the nucleons in a nucleus. When nucleons are added, taken away, or moved around in atomic nuclei, they either give off or take in nuclear energy. This energy is typically millions of times greater than the chemical energy released or absorbed when atoms are added, removed, or rearranged within molecules. Long ago, alchemists sought a way to transform the elements. Now we have finally made their dream come true. Nuclear reactors modify atoms, but they don't turn base metals into gold. They do this to learn more and to release atomic energy. We have a lot of free nucleons that we can put together in different ways to make the atomic nuclei of chemical elements. When free nucleons come together to create a nucleus, it doesn't matter what kind of nucleus it is. Energy is produced because nucleons tug on each other with strong, short-range nuclear forces. The binding energy of the nucleus is the amount of energy that is released when atoms are put together. Every single thing has some energy that holds it together. When a stone falls from space and strikes the ground, it loses its binding energy. Gravity maintains it on the ground. In this case, gravity is what brings things together. The electrical forces that draw atoms together in a molecule are what keep them together. The strong force, also called the strong interaction, is what holds nucleons together in a nucleus. We release the binding energy when we put anything together. We spend the same energy to break it apart as we do to separate it. You can think of the binding energy per nucleon as the total binding energy of the nucleus divided by the number of nucleons. For light nuclei, the binding energy per nucleon rises quickly at the beginning, but it grows more slowly for heavier nuclei. Iron has the most nucleons, 56, and is the heaviest element. After that, its mass slowly falls. For example, 4 iron nuclei release more energy than 1 radium nucleus, with an atomic weight of 224, when there are 224 unbound nucleons. Fission and fusion. Usually we can't start with free nucleons. Finding protons, which are the centers of hydrogen atoms, is not hard. Neutrons, on the other hand, are challenging to detect since they decay and only last approximately 10 minutes when they are free. We need to utilize the nuclei that are already present by either fusing them, a process called fusion, or splitting them apart, a process called fission. The purpose of the nuclear energy game is to increase the binding energy, and the prize is the energy released. When light nuclei fuse into heavier nuclei, energy is released as you move from left to right. When heavier nuclei divide into lighter nuclei, energy is generated. Light nuclei combine to form stars, which release energy. Earth gets nuclear energy by splitting the heavy nuclei of uranium and plutonium. A star on the main sequence creates energy by slowly turning hydrogen into helium. Nuclear reactions in the star's core progressively release this energy, which then spreads out to the surface. Why do stars slowly release nuclear energy? Why doesn't it happen all at once, like a nuclear explosion that lets out a lot of energy? The explanation is straightforward. Protons have a positive charge, and the fact that they repel each other electrically prohibits them from getting too close. In the deep interior of a star, protons with a positive charge flow at speeds of hundreds of kilometers per second. They are always getting closer to one another, but they don't get close enough to spark nuclear reactions very often because they repel each other electrically. We have conceived of protons as objects, like rocks. This is not a correct mechanical picture. People typically picture atoms as miniature solar systems, with electrons orbiting the nucleus like planets orbit the sun. This resemblance gives a misleading impression of the beauty and complexity of the subatomic realm. All subatomic particles, like electrons, protons, and neutrons, act like waves in space. These vibrating waves form several shapes. The electron waves that move around the nucleus determine the size and shape of each type of atom. Like electrons, protons act like waves, but their wavelengths are far shorter than those of electrons. The nucleus is so small because it contains nucleon waves. Particles are different from stones and other things we know about, because they have both corpuscular and wave-like properties, and often behave in ways that are hard to anticipate. When you toss a rock at a wall, it usually bounces back. But a wave, like a radio wave, can travel through the wall and come out on the other side with less power. Because it functions like a wave, a particle like a proton can move through a wall. In quantum mechanics, corpuscles and waves help us understand what we see. A particle acts like a wave, which is why it is spread out in space. The chance of finding it in its corpuscular form at any site is equal to the wave amplitude squared. At the point where the wave amplitude is largest, you have the best chance of finding the particle as a separate item. When you find a particle, such as an electron or a proton, the waves that make it up break down, and the particle becomes a corpuscle. In the corpuscular form, there can't be just a small amount of a particle. It has to be the whole particle, or nothing at all. Think about what happens when a proton hits a wall, like the wall of electrical repulsion that prohibits it from going too close to another proton. The barrier sends the wave back and forth. The wave's amplitude is only 1/10 of what it was before it went through. The chance of discovering the particle is equal to the square of the amplitude. This means that the possibility of detecting it on the other side of the barrier is 1 in 100. There can't be 1/100th of a particle on one side of the barrier and 99/100ths on the other. Therefore, we estimate a 1 in 100 chance of penetration. This means that 99 out of every 100 people who hit the barrier bounce off of it, and 1 goes through. The issues. The first issue is the barrier to repulsion. Every time protons come together, there is a slight chance that the electrical repulsion barriers will let a wave-like penetration through. The chances of penetration are still modest, even at the middle of the Sun, where the temperature is high and protons move very swiftly. Every second, each proton hits other protons head-on about 1 trillion times. It also breaks through a wall that prohibits it from coming too close to another proton. The weak interaction is the second issue. When protons interact after passing through something, they don't react immediately. They break up and go their separate ways till they realize they enjoy each other. Every 10 billion years or so, 2 protons in the middle of the Sun collide and explode. The energy is converted into a particle known as the deuteron. The heavy hydrogen atom has a center called the deuteron. There is 1 proton and 1 neutron in it. Deuterium is the heavy form of hydrogen. The deuteron quickly picks up another proton, which means the second hang-up is no longer an issue. It then releases more energy and transforms into a helium-3 nucleus, which consists of 2 protons and 1 neutron. After that, the helium-3 nuclei quickly come together, releasing more energy, and become the helium-4 nuclei that make up normal helium atoms. The nuclear events discussed are all part of the proton-proton chain. 4 protons come together one at a time in this chain to form a helium nucleus. There are 2 main problems. First, protons with a positive charge have difficulty overcoming their repulsion barriers. Second, even when they do manage to pass beyond these barriers, neutrons are slow to react with each other in a nuclear reaction. This second difficulty happens when a weak force changes a proton into a neutron. This means making a positron, the opposite of an electron, and a neutrino, which has very little mass and moves at or near the speed of light. Stars like the Sun are made up of 1 to 2% carbon, oxygen, nitrogen, and other elements that are heavier than helium. The carbon cycle is another process by which hydrogen is converted into helium in main sequence stars. A carbon-12 nucleus and a proton join together to produce nitrogen-13, which then breaks down into carbon-13. After that, the carbon-13 nucleus joins with another proton to form nitrogen-14, which subsequently turns into nitrogen-15. Finally, the nitrogen-15 nucleus combines with a 4th proton to form nitrogen-16, which is unstable and breaks apart immediately into a helium-4 nucleus and a carbon-12 nucleus. The carbon cycle releases energy at each step, converting 4 protons into 1 helium nucleus. The carbon-12 nucleus speeds up the reaction without being used up. It is harder to get past the electrical barriers of carbon-12, carbon-13, nitrogen-14, and nitrogen-15 than it is to get through the proton-proton chain. This makes it harder to understand the carbon cycle. But after the proton gets over the barrier in the carbon cycle, it might react much more quickly because it doesn't have to make a weak touch with the nucleus for a very brief time. In the carbon cycle, 2 processes are at odds with each other. One increases the size of carbon compounds, and the other reduces their size. The proton-proton chain is the most important thing that happens in lower main sequence stars like the Sun. The carbon cycle is the most important thing that happens in upper main sequence stars. The cores of upper main sequence stars are hotter. In these stars, protons can more readily get beyond the strong forces that keep carbon, oxygen, and nitrogen nuclei apart. In the early 1900s, physicist James Jeans developed a comprehensive theory of fragmentation. He said that the universe used to be full of chaotic gas, and that astronomical systems formed one after the other through a process of fragmentation of nebulae out of chaos, of stars out of nebulae, of planets out of stars, and satellites out of planets. We still believe that galaxies comprise the universe. We used to think that stars broke up into planets, and that planets broke up into satellites, like the Moon. However, we now know that this isn't true. Most of the stars in our galaxy made a long time ago. However, many of them are young, as new stars are still being born at a rate of 1 or 2 every year. Stars are born in the enormous dark gas clouds that are present in space between them. Mostly, these dark clouds are made of hydrogen and helium. Still, they do have a small amount of heavier components, usually dust grains, that make up 1 to 2% of their mass. Young stars are still close to where they were born, and the clouds that made them are still around them. Like the Pleiades, young stars might come from the same dark cloud and clump together. The start of the solar system. The solar system consists of the Sun, Earth, and other planets. It was born some 5 billion years ago, when the universe was barely 1/3 to 1/2 of its current age. We can think of the Sun as a large piece of a cloud that evolved into other blobs, which eventually formed into stars. The blob turned into a protostar, a black, frigid ball of gas and dust that was usually twice the size of the Sun. Helium made up approximately 25% of its mass, and the remaining 75% consisted of heavier elements. We use the present tense as if we were there viewing the scene. At first, the gas globe appears spherical as it spins. However, as the planet becomes smaller, it spins faster and gradually flattens out, assuming the shape of an oblate spheroid. The core, or center of the Earth, rotates faster than the outside parts because it compresses and becomes denser more quickly. The core's contraction slows down over time due to centrifugal force. However, another factor begins to have a significant impact. Ultimately, there is a thick drag that acts like friction. The central regions of the globe spin rather swiftly, which means that gas layers are flowing at various speeds and brushing against each other. This rubbing acts like a brake, reducing the core's spin and shifting its rotation to the outside of the globe. The core continues to become denser due to the action of magnetic fields and viscous forces on it. The gas remains rather chilly outside the core, and its chemical components, which are heavier than hydrogen and helium, tend to clump together to form dust grains. These dust particles, which are typically about 1/1000th of a millimeter wide, collide with each other repeatedly and begin to form clusters. They join together to form tiny bits of meteoroidal rock and ice. Moreover, more than half of this meteoroidal material is frozen water, ammonia, and methane. The rest is metals, their oxides, and silicates. When meteoroids get as big as pebbles, they can move around in the gas and function like little planets. However, as they move through the gas, the friction causes their orbits to become circular, and they settle into a flat disk. Meteoroids regularly bump into each other inside this thin, spinning disk of matter. This happens inside a thick, spinning disk of gas. When they do, they break into smaller pieces, or come together to produce greater particles of matter. The biggest meteoroids eat the most, and the tiniest meteoroids are less likely to break when they hit something. The big meteoroids break down into planetesimals that are hundreds to thousands of meters broad. Most of the time, a lot of meteoroids fall from the sky. Planetesimals can smash against each other and split apart into small fragments, or they can gather together to make bigger bodies. The larger ones battle to stay alive, and those who win take all they can find, becoming the protoplanets. The protoplanets, which are massive bodies like Earth, suck in and hold the gases of the planet, making atmospheres that are full of hydrogen and helium. These atmospheres expand, and the protoplanets develop into large gas giants like Jupiter and Saturn. The Earth's core is also getting denser and hotter, which brings it closer to its final state. The primordial sun has changed that by fusing hydrogen into helium. It is now veiled from view by swirling gas and dust. It can generate a significant amount of nuclear energy. It begins to shake and flare up like a T-Tauri star as it looks for an internal structure that can balance the pace at which energy is lost from the surface with the rate at which nuclear energy is released in the center. T-Tauri is a star that constantly changes shape and size. It is surrounded by gas and dust. It is a new star that is moving closer to the primary sequence of stars. T-Tauri type stars are stars that are like T-Tauri. The primordial sun is erupting as it approaches the main sequence. Its eruptions blast forth a strong wind of fast-moving gas that takes away a lot of materials. The new sun's intense light and strong wind blew the gas globe's leftovers back into space between stars. The planets and the sun are now fighting one last time. The planets attempt to maintain their giant atmospheres, but the intense heat of the sun, accompanied by powerful winds, works to strip them away. The battle is lost by Mercury, Venus, Earth, and Mars, and they are left with only their rocky cores. Because they are farther away and keep their lighter parts for longer, Jupiter, Saturn, Uranus, and Neptune win. The sun finally settles down and goes to bed. The solar system does include a lot of debris from the birth process, though. There are a lot of planetesimals that go around the sun and the planets, and there are also a lot of meteoroids that float across space between planets. At first, the sun and planets quickly clear up this waste, but after a few 100 million years, it slows down. This is the time of bombardment, which lasts for around 500 million years. There are still signs of this time of heavy bombardment on the moon's surface. There are still tens of thousands of asteroids in the space between Mars and Jupiter. They didn't come together to make a planet. There are at least 29 moons around the outer planets, and 3 surrounding the inner planets. The moon is the biggest of these moons. Stars that are smaller than the sun don't change much and stay on the main sequence for more than 10 billion years. A lot of low-mass stars in our galaxy haven't gotten very luminous throughout the years. However, larger stars change rapidly and eventually perish as white dwarfs, neutron stars, or black holes, depending on their size. Now we'll talk about what happens to these bigger stars for a moment. When a star's core runs out of hydrogen, it leaves the main sequence and moves towards the red giants on the HR diagram. The core is now mostly helium, and it no longer generates nuclear energy. However, the star's hot surface continually loses radiant energy, which originates from its core. In response, the core does the only thing it can do. It contracts and densifies, releasing gravitational energy. Due to this constriction, the core's temperature increases. 2 things begin to happen. First, the hydrogen near the helium core begins to burn. A shell that burns hydrogen grows surrounding the core, and helium production remains unabated, adding mass to the helium core all the while. Second, the energy from the core's constricting and the hydrogen burning in the shell around it causes the envelope to grow. The stretched envelope begins to move as the core shrinks and the star expands. The star has become a red giant. It is vast, bright, and chilly. A star is old and doesn't have much time left when it leaves the main sequence. It realizes too late that its time in the main sequence has been dull and uneventful, so it decides to experience one last spectacular moment before it dies. However, there isn't much nuclear energy left. Burning hydrogen into helium has released approximately 80% of the atomic energy that was initially present. You must burn helium in steps to produce nickel and iron, utilizing the remaining material, which is a significant task. The temperatures and densities need to be higher at every step. This causes the star to shine brighter, and it burns out its nuclear fuel at an increasingly rapid rate. White dwarfs. We are referring to a star that has evolved and weighs less than 2 solar masses. Its core continues to shrink during the red giant phase, until, after millions of years, its density and temperature are high enough to convert helium into carbon. Helium starts to burn when the temperature reaches about 100 million Kelvin. This is a helium flash. A mighty stellar wind picks up, and at this time or a little later, depending on how big the core is, the star sheds its inflated envelope, leaving only the bright, naked core. The core stops shrinking, stops using nuclear fuel, and becomes a white dwarf. There is a planetary nebula, a cloud of gas that the star expelled, and a white dwarf, which is slowly cooling and is approximately the same size as Earth. In around 5 billion years, the Sun will turn into a white dwarf. For billions of years, it will be a dim light in the sky, slowly fading away. Supernovae. Now, let's see what happens to a bigger star. It consumes its hydrogen supply in the center faster, and only lives on the main sequence for a few 100 million years. Then it transforms into a giant, enormous red star that lasts only briefly. The helium core becomes smaller and denser as the hydrogen-burning shell around it contracts. The helium quickly changes into carbon and oxygen. The center of the star is made up of carbon and oxygen. It is surrounded by a burning shell of helium and an outer shell of hydrogen that also burns. The star becomes increasingly brighter as it progresses through the red giant stage. It experiences spasms of pulsing and releases a large amount of gas into space very quickly. The core continues to shrink as the demand for energy increases. When the temperature in the heart of the Sun exceeds 3 billion Kelvin and the density approaches 1 million grams per cubic centimeter, carbon and oxygen burn in stages to form neon, magnesium, silicon, phosphorus, sulfur, and other elements. Finally, they make nickel and iron. But the nuclear energy created in all of these reactions doesn't last long. In the later stages of advanced evolution, a steady decline in energy has been occurring, worsening over time. A lot of neutrinos come out of the star in significant amounts. The core and the high-temperature plasma make them. The neutrino brightness in the core rises and surpasses the radiation brightness on the surface. The core shrinks more rapidly to compensate for the energy loss, but the gravitational energy remains constant. The temperature and density in the center rise quickly, and energy flows out and away, making materials that are heavier than iron. In a few seconds, the star will perish. Neutrinos no longer leave the star. Instead, they go away from the core and carry energy that heats the hydrogen-rich outer layers of the star and starts nuclear processes. The core is falling inward and smashing its heavier elements into helium. To let go of the energy that was gathered by combining light components into heavy ones, more gravitational energy must be used. The neutrinos that originate from the core intensify and transform into a blast that propels the expanding envelope into space. When the core starts to implode, helium breaks down into free protons and neutrons in the last few seconds. The energy released over millions of years, while on the main sequence, must be repaid immediately. The core draws this energy from a horrific previous collapse. When electrons are forced into protons, they make neutrons. The core becomes a neutron star when it compresses and loses its outer shell. When the core collapses and the envelope explodes, a significant amount of energy is released. This generates a supernova that shines as brightly as all the stars in a massive galaxy for a short time. A supernova close to Alpha Centauri would be as bright as the Sun. Neutron stars and black holes. A neutron star is a little more than 10 kilometers wide, and its density is about 1,000 trillion grams per cubic centimeter. A thimbleful of neutron matter would weigh 1 billion tons on Earth. The magnetic field of the neutron star is 10 to the 12th Gauss, which is 1 trillion times greater than the Earth's magnetic field. It also spins incredibly swiftly, at hundreds of times per second at first. The star is dead now. The star will live on. A pulsar is what comes out of the ashes of a dead star. It sends out a pulse-like message of things that are under a lot of stress across space. The pulsar has been emitting its rotational energy through electromagnetic waves for approximately 1 million years. This has slowly made it spin less quickly. Neutron stars can't be more than 3 times as heavy as the Sun, because the matter in them can't handle the pull of heavier things. When bigger stars collapse, their cores might not become neutron stars. Instead, they might keep collapsing until they become black holes. In this case, they have to put themselves in their own curved space. A captivating aggregation of black holes may be traversing the core of the Milky Way, inciting intrigue and fascination. At the core of the Milky Way exists an intriguing domain, populated by hundreds of stars, each concealing mysteries poised for discovery. A multitude of others may be hidden just out of sight. At the core of our galaxy resides Sagittarius A. This supermassive black hole influences star formation and changes the cosmos by generating vast gas bubbles in the emptiness of space. However, Sagittarius A star may not be the only black hole in proximity, nor the most dangerous one. For centuries, we have recognized the presence of a supermassive black hole at the center of our galaxy. Nevertheless, it appears that there may be an intense cluster of lesser black holes orbiting it. In February, a team of astronomers from Columbia University disclosed the results of their intriguing exploration near the galaxy's core. Following 12 years of analyzing data from the Chandra Observatory, researchers are endeavoring to elucidate the mysterious nature of star-mass black holes. Upon their demise in magnificent supernova explosions, stars generate intriguing formations, referred to as stellar mass black holes. These emanate from the cosmos. The procedure is straightforward. Stellar mass black holes, measuring only a few tens of kilometers in diameter, pose an almost insurmountable difficulty for discovery. Astronomers are searching for a distinctive type of stellar mass black hole that sheds light on the cosmic unknown. A compelling technique employed to detect stellar mass black holes involves observing their predatory behavior, as they frequently consume companion stars. These vampires constitute an intriguing binary pair. A mysterious black hole, equivalent in mass to a star, engaged in a celestial interaction with a luminous living star. The obsidian void is consuming its counterpart. The black hole functions as a highly fatal parasite for the star. It is stripping mass from the star's surface, and that material is being drawn into the black hole. That stuff ignites with radiance. This allows us to identify black holes not via direct imaging, but by observing fascinating matter as it spirals into them. The difficulty arises from gas and dust permeating the galaxy, blocking the visible light emitted by the binary pair from reaching Earth. Nonetheless, this binary pair releases a distinct form of radiation that traverses gas and dust with exceptional ease: X-rays. The system emits X-rays. Consequently, we designate them as X-ray binaries. The X-ray emissions from these far binaries can be unexpectedly potent and notably observable from our position on Earth. Despite their considerable distance, akin to those situated near the galactic center. The bright matter disks in X-ray binary systems are approximately 1 million times more compact than the accretion disk surrounding Sagittarius A star. The substance surrounding them is so minute that it escapes our vision in complex detail. We perceive X-ray binaries as relatively minor sources of X-ray luminosity. Black holes are the mysterious behemoths of the universe, consuming all matter in their vicinity. Nevertheless, black holes captivate scientists for numerous compelling reasons. They pose an intriguing conundrum for our contemporary comprehension of the world. This occupies the forefront of theoretical physics. In the intricate realm of black holes, it is fascinating to contemplate that our understanding of them may be fundamentally flawed. The complexity of black holes is such that it causes some scientists to question their existence. Despite their formidable reputation, we have not yet encountered one. Black holes reside in the universe, poised for discovery. They are present across the universe. They are dispersed throughout our galaxy, although locating them is a challenging task. In the immense universe, where blackness prevails, the difficulty of distinguishing black from black presents an intriguing conundrum. How do we reveal the concealed enigmas that reside within the universe's shadows? This argument highlights a compelling paradox, since physicists claim that black holes arise from some of the most luminous explosions in the universe, stemming from the remnants of stars that have detonated, with a magnitude much exceeding that of our Sun. A star that radiates luminosity for 10 million years meets a cataclysmic conclusion, collapsing into a black hole within seconds. Upon the fall of the star's outer area, it impacts the core, triggering a magnificent explosion known as a supernova. We witness the explosion, yet the ramifications escape our comprehension. A dormant core, wherein the immense mass of the star is condensed into an almost inconceivable point. A black hole erupts from this little yet potent center, enveloped in mystery. The gravitational force is so powerful that it captures all entities. Even light cannot escape its grasp. How can scientists claim the existence of black holes despite our inability to observe them? That may explore the fundamental nature of our cosmos. For centuries, humans have recognized the existence of atoms, long before we were able to capture an image of one with any apparatus. The concept is analogous to that of black holes. Merely because it is concealed does not imply it is not present in the shadows. Although black holes are imperceptible, their existence is as indisputable as the wind, which, though unseen, is experienced in every breath we inhale. Although air is invisible, its presence is revealed through the intriguing effects it produces when in motion. Black holes are a fascinating mystery. It is essential to understand what to look for upon their release. Black holes are enveloped in obscurity, yet they emit remarkable streams of X-rays that fascinate the mind. This is attributable to their inability to self-emit light, yet they function as intriguing generators of X-rays. As particles approach a black hole, the formidable gravitational force accelerates them, raising their temperatures to extraordinary millions of degrees. When gas attains millions of degrees, it emits a deluge of X-rays, producing a remarkable display of cosmic energy. Researchers utilize the New Star Satellite Telescope to detect and quantify these illuminating X-rays. In February 2017, an intriguing emission of X-rays was observed in the cluster designated 47 Tucana, situated near the periphery of the Milky Way. Upon examining the data, astronomers discovered an intriguing finding. Two celestial bodies participate in a close orbital interaction. We witness the enthralling collapse of a star as gas spirals and descends into an enigmatic dark void. An unexpected occurrence is transpiring. When one object accretes matter from its companion, it induces a captivating emission of X-rays. Researchers can use such X-rays to determine the orbits and measure the mass of the objects. Researchers investigating the measurements of these celestial bodies have discovered that the first is a faint relic of a star similar to our Sun. Despite its small size, the second object has a mass comparable to that of a massive organism. Could this be an enigmatic black hole concealed in the cosmos? We are examining an object that has substantial mass, is exceedingly small, is highly dense, and exerts a strong gravitational force. Nonetheless, other intriguing techniques exist for fabricating such a thing. A neutron star is a captivating and mysterious creature in the cosmos, characterized by its extreme density, which evokes interest and intrigue. Neutron stars originate through a fascinating mechanism, much like one that is thought to produce black holes. Upon concluding their life cycle, stars undergo a magnificent explosion, subsequently collapsing into a small, dense sphere of mass. Light successfully escapes. Black holes and neutron stars have an intriguing familial relationship. Nevertheless, a neutron star lacks the requisite mass to undergo a tumultuous collapse. Envision a neutron star precariously balancing, adeptly evading the gravitational force that could ensnare it within a black hole. What an enthralling situation. The little object revealed by New Star possesses an extraordinary mass. However, possessing size and mass alone is insufficient to validate its classification as a black hole. Cosmologists are pursuing a deeper understanding. Although black holes elude direct observation, does there exist another method to reveal their mysteries? What if they were eavesdropping? Envision the profound consequences of two massive vehicles colliding. Bang! A captivating sound arises when they do. Subsequently, we can ascertain whether the accident occurred and, if so, investigate the intriguing specifics of its nature. It is analogous to the enthralling occurrences that transpire during the merger of black holes. Could the auditory phenomenon of a black hole collision serve as the definitive evidence for their existence? Black holes stand as mysterious giants of the universe, although our comprehension is cloaked in intriguing suggestions rather than definitive evidence of their existence. Cosmologists are engaged in a thrilling pursuit, investigating the mysterious realm of gravitational waves in search of substantial evidence. Gravitational waves continuously traverse this chamber, creating an invisible tapestry of cosmic fascination. With each delicate motion of my hands, I make a disturbance in the fabric of space-time, producing gravitational waves that traverse the cosmos. The difficulty arises from the exceedingly weak nature of gravity, rendering its forces challenging to detect. Undulations. To elucidate the mysterious disruptions in the continuum of space and time, one must seek cataclysmic occurrences involving massive entities. Black holes, the mysterious behemoths of the universe, are among the most dense phenomena in existence. This presents an intriguing prospect. We may observe the ripples in space-time produced by their violent clashes. LIGO, the Laser Interferometer, Gravitational Wave Observatory, detects gravitational waves that may emanate from almost 1 billion light-years away. In 2017, LIGO identified a significant collision. Astronomers have discovered enormous supermassive black holes residing in the early universe. This is a fascinating mystery. It is intriguing to contemplate that supermassive black holes, which appear highly implausible, indeed originated in the early cosmos. What secrets do they possess? It is perplexing how they expanded at such an extraordinary rate, contravening the principles of physics. For astrophysicists, deciphering the mystery of how black holes have grown to such immense sizes is an intriguing challenge. We must investigate other methods for nurturing these tremendous black holes. A different mechanism must exist that allows them to attain that bulk at such an early stage. What might that be? The extensive night sky discloses merely 4.8% of the universe's total stuff. What exists beyond the observable? The enigma intensifies. The remainder exists inside the mysterious vastness of the universe, including the elusive dark matter. The existence of dark matter, however imperceptible and undetectable, is an apparent riddle that intrigues us. The gravitational pull attracts all nearby objects, generating an irresistible force that fascinates the imagination. We are beginning to reveal its fundamental role in forming the universe. A substantial fraction of the cosmic substance that aggregates via gravitational forces remains enigmatic and is referred to as dark matter. Is it possible that black holes originate from intriguing interactions with dark matter? Consider this. A substantial quantity of dark matter exists, surpassing regular matter by a factor of 6. Envision a situation in which black holes might consume 6 times more matter if they could utilize this mysterious dark substance present in the universe. Is it possible that these massive black holes are growing by consuming dark matter? The prospects are intriguing. There are several intriguing clues. The largest supermassive black holes are not located in galaxies abundant in typical matter. They inhabit galaxies obscured by the mysterious depths of dark matter. Current understanding of dark matter suggests that it exhibits gravitational properties, which are notably similar to those of a black hole. It attracts all entities possessing substance. Therefore, it is imperative to re-evaluate the concept that black holes solely consume ordinary matter, especially in light of our present comprehension of the substantial quantities of dark matter present in the universe. Is it possible that dark matter contributes to the heating of black holes? The potential is intriguing. In some respects, dark matter may serve as fuel for these massive black holes. Is it possible that the creation of a supermassive black hole is affected by the directed flow of ordinary matter? Dark matter is the invisible force that discreetly alters the equilibrium, facilitating the seamless progression of the event. Researchers are beginning to reveal that dark matter may serve as the spark for the production of large black holes via the ignition of dark stars. Some theorize that dark matter catalyzed the formation of the universe's primordial superstars. Upon their death, they leave us with enigmatic, supermassive black holes. Dark stars seem like a notion derived from science fiction. Still, Dr. Katie Fries posits that they may be crucial to understanding the rapid expansion of primordial, supermassive black holes. Dark stars are undeniably enchanting. Our excitement escalated when we envisioned this concept, centered on a newly identified form of star that has yet to be observed. Could dark stars be among the earliest entities to arise in the universe? The possibilities are both intriguing and mysterious. They illuminated with brilliance when the universe was only 200 million years old. What a fascinating inquiry! In what manner could dark stars lead to the formation of massive black holes? A newly generated black hole cannot surpass the mass of its progenitor star. To form a supermassive black hole, the progenitor star must have substantial mass. These primitive artifacts are quite enthralling. They are remarkably intriguing and quite huge. These objects are exceptionally immense, measuring 10 times the distance between our Sun and Earth. How is that possible? Common stars have a definite maximum size limit. A star is an intriguing conflict of forces, wherein the unyielding force of gravity contends with the explosive energy of nuclear fusion. What an enthralling conflict. As the star expands beyond its boundaries, the force of its gravity becomes inescapably powerful. The delicate balance of gravity and fusion has been disturbed. The inexorable force of gravity prevails, resulting in the star's catastrophic demise. Nevertheless, dark stars may have an ingenious mechanism that allows them to evolve into supermassive forms. Consequently, they consist of the familiar substance we encounter. Although hydrogen and helium constitute their fundamental nature, it is the elusive power of dark matter that genuinely propels them. Although the essence of dark matter remains elusive, our theories suggest its fascinating potential to energize a star. The elusive, weakly interacting, massive particles, referred to as WIMPs, are primarily believed to constitute the majority of dark matter. Consequently, these WIMPs possess enigmatic counterparts in antimatter. Upon collision, they undergo a profound transformation, metamorphosing into an entirely distinct entity, while releasing a significant amount of heat and energy. It is that enchanting energy that may ignite the luminosity of stars. The energy produced by the WIMP's annihilations inhibits the star from undergoing the conventional collapse that most stars encounter. Envision a situation in which the mysterious force of dark matter powers the core of specific stars. Captivating. Envision a realm where the imperceptible energies of the cosmos catalyze extraordinary phenomena, culminating in the formation of colossal black holes upon their eventual dissipation. What enigmas exist within this cosmic phenomenon? The mysterious characteristics of dark matter may be crucial in comprehending the formation of black holes and their prevalence in the universe. The enigmatic energy derived from dark matter allows dark stars to grow to immense dimensions. In their first phases, they seem comparatively small. Envision cosmic behemoths, initially like our Sun, whose cooler temperatures enable them to accumulate matter, perpetually expanding without limit. Certain of these mysterious creatures may ultimately attain a mass 1 million times greater than that of the Sun, and emit luminosity 1 billion times more intense. Nevertheless, these immense entities possess a transient existence. Ultimately, the elusive dark matter particles annihilate each other, resulting in a lack of fuel to sustain the substantial amounts of conventional matter. Deteriorating. And then, just like that, it concludes. This vast, voluminous monster eludes description. Upon attaining a certain magnitude, one is inexorably drawn into a black hole. What we possess here is an extraordinary, supermassive black hole. The entity under discussion is a supermassive black hole. The mysterious properties of dark matter may be affecting stellar energy. If this is the case, it presents an intriguing new perspective on our understanding of stars and their evolution over time. The concept of dark stars currently resides solely within theoretical frameworks. Nonetheless, with the activation of the mighty James Webb Telescope in 2018, we may be on the verge of discovering something very intriguing. We are poised to launch an exciting observational campaign to uncover intriguing discoveries. Consequently, we are elated. Uncovering a completely novel type of star would be momentous. While Katie Fries investigates the mysterious domain of dark stars, another team is examining an innovative concept that sheds light on the remarkable expansion of supermassive black holes. They detect the faint murmurs of a catastrophic event from the distant expanses of the universe. The aftermath of a significant confrontation is a highly dynamic event that reveals the insatiable nature of black holes. It is intriguing to learn that ultramassive black holes, with masses billions of times greater than that of our Sun, exist. Nonetheless, the enigma of how they attained such extraordinary mass remains unresolved. We have discovered the intriguing occurrence of lightweight stellar mass black holes merging. An intriguing occurrence transpired as they merged into a massive black hole, releasing an extraordinary burst of energy. What is the nature of supermassive black holes? During galactic collisions, the supermassive black holes in their centers converge, spiraling into the nucleus of the newly formed galaxy. Could supermassive black holes involved in galaxy mergers coalesce to become an ultramassive black hole? In 2017, the Hubble Space Telescope identified an intriguing anomaly in the faraway galaxy known as 3C186. A remarkably luminous point was identified, situated thousands of light-years from the core of the galaxy. Researchers suspect it may be a quasar. A quasar is an exceptionally luminous active galactic nucleus, powered by a supermassive black hole at its center. Quasars, powered by black holes, have repeatedly been observed, but until recently, they have only been found near the centers of galaxies. Upon obtaining this data from Hubble, we were astonished to find that the quasar we had presumed to be at the center of this galaxy was absent. This black hole is located approximately 35,000 light-years from the center of the galaxy, eliciting curiosity and fascination. That is rather intriguing. Identifying a quasar, a supermassive black hole located far from the galaxy's core, is a rare and intriguing phenomenon that sparks curiosity. Upon further investigation, researchers discovered that the quasar was rapidly traversing the cosmos, moving away from the core of the galaxy. A black hole, with a mass approximately 1 billion times that of the Sun, is traversing space at an extraordinary velocity of 4 million miles per hour. This mysterious black hole, which likely originated at the galaxy's core, has given rise to an extraordinary phenomenon. An object accelerated to remarkable velocities, the consequence of a cataclysmic event shrouded in mystery. Envisioning the kind is tough. What type of event may generate sufficient energy to expel such a massive object from the core of a galaxy? Who propelled it into the air? What caused its ejection? And what were the fundamental reasons? Researchers are investigating a fascinating phenomenon. 3C186 may be an intriguing remnant of a galactic collision. During the collision and merger of galaxies, supermassive black holes participate in a cosmic interaction, circling each other and emitting intense energy bursts that propagate through spacetime as gravitational waves. Gravitational waves traverse the fabric of our cosmos, an invisible phenomenon that ignites curiosity and awe. They are nuanced disruptions in the fabric that generate imperceptible waves. The merger of supermassive black holes releases a remarkable quantity of energy as gravitational waves, producing a mesmerizing phenomenon in the universe. Researchers hypothesize that these mysterious black holes may display an intriguing variety of sizes. The interaction between a massive black hole and a smaller one can result in a fascinating phenomenon: the asymmetric emission of gravitational waves during their spiral dance and subsequent merger. This disparity results in significant repercussions. Upon the collision of the two black holes, a substantial release of gravitational waves occurs, although it is noteworthy that these waves propagate in a singular direction. This influx of energy drives the recently amalgamated black hole away from the galaxy's core. Envision a tremendous impact, comparable to the recoil of a shot gun, but amplified to an unbelievable magnitude. The immense power of such emission is remarkable. It drives the combined black hole like a cosmic rocket, propelling it through the universe. It would have been a thrilling, unprecedented show. They possess an exuberant vitality. They are unwinding the fundamental threads of the universe. Although we did not see the collision directly, the existence of 3C186 may imply that supermassive black holes can collide and merge, possibly resulting in the formation of even larger black holes. This intriguing method may facilitate the formation of an ultramassive black hole. The ejected black hole, driven by gravitational forces, commenced a solitary voyage into the unknown. Envision a supermassive black hole being disturbed by gravitational waves, traversing the cosmos in an exhilarating celestial ballet. It is projected to extricate itself from its galaxy in 20 million years. The ejected supermassive black hole may eventually collide with another galaxy, resulting in an intriguing merger with its supermassive black hole. An intriguing emptiness. The most powerful black holes seem to impose their dominance, controlling galaxies and even other black holes in a cosmic interplay of strength. Researchers have just discovered a black hole that is insatiably consuming the resources of a neighboring star, reminiscent of a cosmic vampire. Ultramassive black holes possess a remarkable propensity to annihilate host galaxies, while supermassive black holes appear to regulate the process of star formation. Can we genuinely see all supermassive black holes as benevolent entities? A myriad of galaxies, both large and small, orbit the Milky Way. The majority of the largest galaxies display a pronounced red coloration. This is an ominous sign. In the expanse of space, the hue red evokes an exhilarating sensation of danger. The active process of star formation results in the creation of massive stars. These gigantic giants frequently emit vibrant blue radiance, yet their lifespans are ephemeral, concluding in magnificent explosions. Upon the cessation of star production, after a designated interval, the galaxy acquires a pronounced red coloration. The final celestial phenomena in our universe are the diminutive, persistent red stars known as red dwarfs, remarkable for their exceptionally long lifetimes. A galaxy suffused with crimson tones, inhabited exclusively by red dwarfs, suggests a narrative of deterioration and diminishing luminosity. In February 2017, a group of astronomers delved into the mysterious depths of the dense star cluster 47 Tucanae, situated near the outskirts of the Milky Way galaxy. They identified 25 pulsars, intriguing celestial entities that rotate and emit radiation, serving as cosmic markers in the vast expanse of space. These pulsars are all orbiting a central mystery. Despite the central object being obscured from our sight, we were able to observe its intriguing activity through the orbits of the surrounding pulsars, allowing us to infer its dimensions. Upon analyzing the data, one discovers a mass around 1,500 to 2,000 times higher than that of our Sun. At the center of the globular cluster, a mysterious object lies in wait for detection. What might this invisible thing be? An immense and obscure entity is likely concealed at the core of 47 Tucanae, awaiting discovery. Astronomers appear to favor the hypothesis of a colossal black hole residing in the recesses of space. This monster, with a mass 1,500 times that of the Sun, poses an intriguing conundrum. It is considerably larger than a standard star black hole, yet insufficiently huge to be deemed supermassive. What might it be? The enigma persists in intensifying. Could this item be an intermediate mass black hole? Identifying these mysterious intermediate mass black holes presents a significant difficulty. This atypical black hole possesses a mass equivalent to that of a solitary sun. At that magnitude, they could have swiftly transformed into supermassive beings. Could intermediate mass black holes be pivotal in elucidating the mysteries of supermassive black holes? Supermassive black holes may possess a compelling advantage from the onset of their existence. Astronomers have embarked on an exhilarating expedition through the cosmos, elucidating the universe's mysteries and sparking curiosity about the unknown. cosmic explorers investigate the mysterious domain of intermediate mass black holes. They may have been significant enough to constitute the foundational elements for the initial supermassive black holes. Nevertheless, they persist in evading detection. They represent a crucial aspect that has yet to be revealed. They have disappeared. Envision yourself as an extraterrestrial visitor arriving on Earth, possessing only a limited comprehension of the enigmatic entities referred to as humans. Your attention is captivated by the diminutive, inquisitive children and the imposing silhouettes of grown-ups. No adolescents are seen. It is intriguing to contemplate how small children evolve into fully developed adults, although the process of this metamorphosis remains enigmatic. Is that not intriguing? The incremental changes frequently remain unobserved. That would be rather intriguing. Is that not intriguing? This is the situation with supermassive black holes. Envision a universe lacking the exuberant disorder and inquisitiveness characteristic of adolescence. Such was the perception till September 2020. Researchers investigating gravitational waves have detected an intriguing signal originating from a cataclysmic event in the distant universe. Researchers are investigating intriguing phenomena referred to as gravitational waves. They resemble waves reverberating across the universe's fundamental structure. Numerous signals emit an enchanting chirp. It is a recognized sound. It develops unexpectedly. Nonetheless, this particular event was so powerful and sudden that it resembled a jarring thud. The remote thud emanating from the furthest expanses of the universe serves as an intriguing signal for those pursuing intermediate black holes. One can get a particular conclusion from its pitch. Envision the cosmic event that transpires when two massive black holes merge, forming a single entity with a mass 142 times that of our Sun. What an unusual phenomenon to contemplate. We are entering the domain of intermediate mass black holes for the first time. This signifies the moment we have conclusively identified an intermediate black hole for the first time. Revealing direct evidence for an intermediate mass black hole is exceptionally intriguing. With the validation of intermediate black holes, may they elucidate the mystery of supermassive black hole development in the early universe. Are these intermediate black holes maybe the fascinating initial seeds of supermassive black holes? The enigma intensifies. To elucidate the mystery of the rapid emergence of these huge supermassive black holes following the Big Bang, one would need something remarkably unusual. What are the origins of intermediate black holes, and how do they form? A remarkable discovery has emerged from the collision of two tiny black holes in the cosmos. They may also arise from immense gas clouds enveloped in mystery. In the ancient cosmos, vast gas clouds possessed the extraordinary capacity to expel energy swiftly and unpredictably, resulting in the fascinating emergence of a black hole of this scale. The expansive gas cloud condenses and densifies, a process similar to that involved in the formation of stars. Nevertheless, it intriguingly preserves its coherence, finally converging into a massive entity that results in an intermediate mass black hole. A massive gas cloud descending into an intermediate mass black hole would be a remarkable phenomenon. It appears to me that what we perceive as a vast cloud progressively yielding to a black hole resembles a substantial region populated by black holes themselves. One day, you find yourself observing the catastrophic collapse of a massive gas facility. You are now gazing directly into the abyss of a colossal black hole. That is the minimum. Hypothesis: the formation of a black hole via the direct collapse of a gas cloud poses a fascinating task replete with enigmas. Gas clouds frequently fragment and undergo a remarkable transformation, resulting in the formation of many stars. Extraordinary circumstances would be requisite to amalgamate into a singular organism. Envision a mesmerizing scenario in which two adjacent galaxies engage in a celestial ballet. Envision a nascent proto-galaxy, an enigmatic gas cloud, poised to initiate stellar formation inside its confines. A colossal galaxy resides nearby, enveloped in intrigue. It is generating an extraordinary quantity of stars, with radiation shooting in all directions towards its youthful counterpart. As they are readily accessible, the cloud becomes denser and more substantial until it reaches a threshold where gravitational forces dominate. The cloud evolves into the intriguing domain of star formation. As the gas cloud expands and densifies, gravitational forces begin to exert their enigmatic influence, pulling it inward in a mesmerizing cosmic interplay. The failure to ignite into stars results in the formation of an intriguing intermediate mass black hole. This thought is quite intriguing. Although it is conceivable, numerous uncertainties persist concerning the early cosmos. Regardless of the origins of these intermediate mass black holes, they represent a compelling avenue for elucidating the mystery of supermassive black holes in the early universe. The compelling question pertains to their growing process. How does one commence with this minuscule seed and finally produce something that weighs 1 billion times more than the Sun? Early intermediate mass black holes may have exhibited voracious appetites, consuming all available matter to attain a supermassive state, partaking in the most substantial resources the cosmos provides. We have explored the expanse of the M87 galaxy, yet the enigmatic supermassive black hole remains an intriguing mystery on the horizon. From our perspective, M87's star may seem minor, although it possesses an astonishing mass of 6.5 billion solar masses. What circumstances contributed to the remarkable expansion of M87's supermassive black hole? One of the intriguing mysteries that persists is what determines the size of massive black holes located at the centers of galaxies. It is intriguing how it closely correlates with factors such as the galaxy's dimensions. More extensive galaxies contain substantial black holes. To elucidate the enigma of the M87 star's immense growth, we must investigate the intriguing history of its galaxy. We must verify the accuracy of the extensive expansion of the M87 host galaxy. M87 is immense. A massive black hole lies hidden in this expansive galaxy, enveloped in mystery. It is vast. This is a compelling instance of a brightest cluster galaxy, which is acknowledged as one of the largest galaxies in the universe. Typically, a galaxy of M87's mass would be significantly more compact. Instead, M87 is notably expansive. What is the rationale for that? A hint arises from the configuration of the M87 stars. During our exploration of the galaxy, we find that the stars are distributed in an area 100 times larger than we had expected. What factors may have contributed to the dispersion of stars around the cosmos? Galaxies are perpetually in motion. Each galaxy traverses the cosmos, occasionally approaching one another and participating in intriguing interaction. Substitute. The term interact conveys passion and interest, prompting curiosity and further investigation. Galaxies are colliding in a chaotic cosmic interplay. They are consuming smaller galaxies or breaking them down. Occasionally, they may induce intriguing anomalies in the formation of faraway galaxies through drive-bys. Galaxies occasionally engage in dramatic interactions, colliding and merging into a singular entity. The merging process incorporates new gas and stars, resulting in the growth of galaxies. Galactic cannibalism transpires with greater regularity than one might anticipate. Is it possible that the M87 galaxy consumed its celestial counterparts? How can we ascertain the truth? Identifying stars that originated from consumed galaxies poses a significant problem, fraught with complexity. When endeavoring to delineate a distant galaxy, utilizing the energy of its stars poses a significant dilemma. They integrate effortlessly into both the foreground and the backdrop. It is a considerable enigma to ascertain evidence of the galactic merger's occurrence. All elements have been refined to excellence. It resembles the act of pouring water into a tranquil pond, generating ripples that draw inquiry. Once the waves subside, distinguish the water molecules originating from the bucket from those sourced from the pond. What is before you is simply a tumultuous amalgamation of water, akin to the captivating distribution of stars dispersed throughout a galaxy. What methods can be employed to discern water from a pail submerged in the enigmatic depths of a pond? We must identify indicators of disruption, such as ripples or distinctive patterns of sand and mud disturbed by the event. Galactic collisions can produce a captivating relic that radiates luminously, like a planetary nebula, celestial nebulae of gas and dust. These radiant marks enable precise navigation of the galaxy, revealing hidden mysteries within the cosmos. Imagine a celestial phenomenon in which a medium-sized star, approaching the conclusion of its life cycle, spectacularly expels its outer layers in a stunning exhibition. A planetary nebula develops when a star depletes its fuel, resulting in a remarkable alteration in the universe. The mysterious external layers erupt, forming a nebula that often assumes the enchanting shapes of a ring or bubble. Envision observing a magnificent luminous blue-green entity departing from the star, enthralling your mind. These are far larger than stars. They are exceptionally prominent. A crew embarked on a thrilling expedition to reveal the mysteries of planetary nebulae concealed within the M87 galaxy. During their astronomical survey, they discovered 300 distinct bright points. The blue-green spots indicate their identity as planetary nebulae, eliciting curiosity and awe. Planetary nebulae are exceptionally intriguing. They radiate an enigmatic luminosity throughout the expansive cosmos. The nebula's movements are strikingly contrasted with the stars in M87. This indicates that their origins are rooted in a more compact, youthful galaxy rather than M87. The existence of these planetary nebulae indicates that an intriguing event transpired in this ancient, desolate galaxy. What might it have been? An enthralling confrontation occurred as two galaxies merged in the expanse of space. The discovery regarding planetary nebulae suggests a captivating occurrence that has taken place over the past billion years. M87 consumed a smaller galaxy. This galaxy approached dangerously close to the colossal M87. In the 1980s, a formidable gravitational force drew the smaller galaxy inexorably closer with an irresistible attraction. Envision observing a galaxy expanding in real time, transforming into novel and unforeseen shapes as it extends across the firmament. As the galaxy neared, it would begin to distort, causing your galaxy to contort in reaction, converting the sky into a captivating tableau of glimmering stellar streams. M87 ensnared the tiny galaxy, completely engulfing it in its cosmic grasp. Is there anything more enthralling than the collision of two galaxies? The turbulent history of mergers reveals the mysteries underlying the immense scale of the M87 galaxy. Each event attracted numerous cosmic marvels. The collisions generated immense gravitational forces, propelling stars across space, akin to confetti in a cosmic party. After an event of this scale, the stars are expected to be dispersed throughout the sky, with their separations from one another augmented by a factor of 10 to 100 relative to their prior configuration. Certain collisions propelled stars into the galaxy. Certain collisions altered the galaxy's fundamental structure. Envision a far galaxy that exhibits a sleek, unembellished oval shape. Most galaxies have a supermassive black hole at their core, including those that have engulfed M87. What is the narrative behind those mysterious black holes? Is it possible that they amalgamated with M87, resulting in an expansion of its dimensions? M87, being an elliptical galaxy, implies that it has undergone multiple mergers of supermassive black holes, providing a persuasive rationale for its substantial mass. In sharp contrast to its turbulent history, the M87 galaxy presently has an unexpectedly tranquil appearance. M87's supermassive black hole is thought to have increased in size by assimilating other supermassive black holes, which were attracted during galaxy collisions. However, the rationale for this phenomenon remains unclear, as the principles of physics suggest that supermassive black holes are not intended to coalesce. Rather, they interlace in a perpetual cosmic dance, enveloped in mystery. Upon the demise of a massive star, it triggers a supernova, an explosive occurrence that is among the most remarkable events in the cosmos. What is the progression from a tumultuous decline to a spectacular emergence? This explores some of the most complex astrophysics ever discovered, and the intricacies of the process remain enigmatic. An elusive factor is involved, as we invariably identify supernovas after they have occurred. You are observing the star's brilliance intensifying, which is occurring intriguingly after the event itself. The genuine fascination resides not in the discovery of a supernova, but in identifying the critical moment known as the breakout. The explosion signifies the dramatic end of a colossal star's life cycle. It is the mesmerizing moment when the core collapses, resulting in the star's spectacular outpouring of radiant light. Throughout its extensive history, astronomy has captured this remarkable moment on only 2 occasions. In an astonishing turn of events, NASA's multi-million-dollar space telescope, Kepler, captured this singular moment. Nevertheless, an extraordinarily fortunate Argentinian amateur succeeded in capturing it a second time. This narrative enthralls me. Introducing Victor Busso, an avid amateur astronomer with a fervent interest in the cosmos. A magnificent telescope resides in an enigmatic observatory within his garden, poised to reveal the universe's mysteries. He continuously captured images of the same galaxy that was inexplicably suspended overhead. He inadvertently looked at the optimal section of the sky, allowing him to observe the remarkable moment of a supernova's shock breakout. Seizing this moment is an exceedingly elusive endeavor. Victor captured the moment the shockwave arrived. The external layer. Victor identified a mysterious anomaly appearing in his images. Upon realizing he had captured the early explosion of a dying star, he promptly contacted an expert. In an exhilarating turn of events, the telescope focused on a remote galaxy and, within barely an hour, revealed a magnificently detonating star. It is an intriguing puzzle awaiting resolution. Alex Filipenko and his crew observed a remarkable increase in luminosity from the star. During our investigation of Busso's supernova, we discovered an intriguing phenomenon. The object underwent a sudden and intense luminosity increase for a brief duration, triggered by a shock wave. A supersonic wave emanated from the star's surface. As we near the precipice, a brilliant explosion releases an extraordinary surge of energy. At that moment, the unforeseen occurs. A massive shock wave travels at an extraordinary 30,000 miles per hour, emanating from the star's surface and disintegrating it in a magnificent spectacle. Commencement. We observe the intriguing waves generated by earthquakes and other explosions on Earth. They can traverse gas, liquid, and solid, even infiltrating the core of a collapsing star. Victor's observation of the shockwave impacting the star's surface was extraordinary, as he experienced its metamorphosis into a supernova in real time. We must investigate this extraordinary finding. The shock breakout is a transient and intriguing phenomenon, enduring merely 20 minutes within the vast context of the universe. What factors could initiate the shockwave? Could it simply be a question of rebound? Envision deciphering the cosmic mystery of a supernova shockwave via the perspective of a basketball. Captivating. Envision a star erupting in radiance. Nuclear reactions initiate in the core, generating shockwaves that propagate outward through the outer layers. These layers subsequently descend inside at remarkable velocities, only to bounce and surge outward in a magnificent cosmic display. The star's composition is the source of its remarkable energy. As the diminishing star depletes its energy, it intricately interlaces a variety of elements. At the core of the star resides a dense iron nucleus, surrounded by an intriguing assortment of lighter components that invite investigation. Envision a situation involving a solitary layer, followed by an intriguing rebound, akin to the action of dropping a ball. Although it may not rebound with significant force, it is seen as organized, akin to a celestial body, with denser materials situated beneath and lighter elements suspended above. Let us examine and clarify the process by which this resurgence occurs. That was an extraordinary resurgence. The tennis ball is launched into the air, driven by the energy generated from the basketball's bounce, resulting in an intriguing interaction of forces. In a collapsing star, a comparable event occurs, albeit with more layers involved. All the disparate elements coalesce, forming an enigmatic convergence. The denser layers initially impact the core, transferring energy to the lighter layers, which subsequently produce the shockwave. Nonetheless, this energy is insufficient to propel the shockwave beyond the star's boundaries. Upon further examination with our computational models, the results did not align with our expectations. The shockwave seemed to halt. We could not initiate the star's tremendous metamorphosis. For 50 years, the elusive component of the puzzle remained unattainable. Researchers hypothesized the existence of a subtle, practically imperceptible component influencing the situation. Could a specter be present within the supernova apparatus? October 2019. One of the most brilliant lights in the night sky is ensnared in an intriguing struggle. Observe the constellation Orion, and you will find that one of its shoulders is embellished with a prominent crimson star. Welcome to the intriguing realm of Betelgeuse. Upon exploring my property, I discovered something fascinating. The light was progressively diminishing, creating an atmosphere of ambiguity. Could this indicate a more significant issue? Is Betelgeuse nearing its ultimate phase? Betelgeuse, a massive star, possesses a mass approximately 15 to 20 times that of the Sun, and is nearing the conclusion of its life cycle. Betelgeuse, a massive and luminous star, is poised for a remarkable explosion. Betelgeuse commands our interest as a leading candidate for a supernova due to its immense size. The greater the star's mass, the more ephemeral its lifespan. The existence of a star depends on a captivating interaction between two contrasting forces. The interaction of heat and pressure exerts an outward force, whereas the unyielding force of gravity pulls inward. Stars illuminate the cosmos, sustained by forces that keep them in their positions. Support structures do not maintain their elevation. The energy emanating from the core to the star's surface sustains their buoyancy in the cosmic ballet. That ceases the attraction of gravity's grasp. In the core of stars, a captivating process occurs when hydrogen atoms smash with immense force, fusing to form helium. The mesmerizing process of nuclear fusion is the fundamental origin of their luminous energy. Consequently, what is occurring in this situation? An increased amount of hydrogen indicates that a star possesses more material, hence prolonging its lifespan in the cosmos. The circumstances are completely inverted. What might it be? This force, which anchors humanity, remains a mystery in the universe. The mass of a star directly correlates with the strength of its gravitational attraction. The gravitational pull compresses its hydrogen atoms in greater proximity. The gravitational force compels hydrogen atoms to converge more closely. As you persist in crushing materials, the temperature rises significantly, triggering nuclear fusion events that accelerate swiftly. Consequently, larger stars deplete their fuel at an extraordinary pace, resulting in relatively brief lifespans. Smaller stars utilize their fuel gradually, resulting in prolonged and intriguing lifespans. Consequently, a noteworthy star experiences a rapid life cycle, culminating in a fast extinction. Betelgeuse radiates with a luminosity of 125,000 suns, yet it is exhausting its hydrogen supplies, turning to combusting any remaining material to sustain its survival. Stars function as cosmic laboratories, converting hydrogen into helium via a remarkable fusion process. Upon depleting helium, stars initiate a remarkable process, fusing heavier elements such as carbon, nitrogen, and oxygen in an intriguing cosmic sequence. It is comparable to incinerating an object, producing ash, but if the ash is finely ground, it may ignite again. Subsequently, you further grind the ash, preparing it for another phase of combustion. However, this trip cannot continue indefinitely. As the size of the fused atomic nuclei increases, the released energy decreases. The fundamental energy sustaining the star's resistance to gravity is diminishing. Unfortunately, as larger nuclei are fused, the energy that can be extracted decreases markedly, ultimately leading to the formation of iron, which notably represents the last element created by this process. The intriguing characteristic of iron is its behavior during fusion. Instead of producing energy, it absorbs it. What a fascinating development in the realm of components. Upon the accumulation of an iron core, the star's destiny is irrevocably determined. The star has reached a stage where it can no longer generate sufficient energy in its core, resulting in a captivating yet foreboding collapse as internal forces struggle to preserve equilibrium. Thus, their strategy is to induce collapse. In an extraordinarily brief instant, the star's core collapses, reducing in size from that of a planet to that of a small city. When that occurs, a tempest of exhilaration ensues. The unforeseen surge of energy drives the internal layers outward again. What we observe is a monumental explosion, a phenomenon referred to as a supernova. A supernova emits a shock wave that propagates outward at remarkable velocities, attaining thousands of miles per second. For a brief instant, they radiate a luminosity that surpasses that of an entire galaxy. A supernova might potentially devastate life on Earth, with indications of this impending catastrophe concealed under the depths of our oceans. Deep beneath the surface, an intriguing narrative emerges, characterized by many strata of silt. A notable stratum, approximately 2.6 million years old, exhibits an extraordinary abundance of the rare chemical element iron-60. Iron-60, a remarkable radioactive isotope of iron, has a notably short half-life of around 2.6 million years. A supernova, an explosive phenomenon that occurs after a star's demise, is the only known source of iron, 60. This indicates that a supernova likely transpired in proximity within the last few million years, depositing remnants of its cosmic material on Earth. That evokes a shiver along my spine. A subtle layer of this uncommon type of iron signifies this remarkable assault on our environment. It resides concealed in the abyss of each oceanic floor, invariably located at the same enigmatic depth. Envision a massive influx of cosmic dust descending upon our planet, an occurrence that occurred approximately 2.6 million years ago, shrouded in mystery and fascination. It was a bewildering time replete with ambiguity. 1/3 of the ocean's magnificent animal species have disappeared in an unforeseen occurrence. There were some extraordinary fish. The megalodon is a captivating beast, an immense shark with teeth akin to dinner plates and much more. However, they disappeared from existence 2.6 million years ago, signifying the end of the Pliocene epoch. What occurred? A captivating occurrence transpired as numerous marine organisms succumbed, with a notable concentration of fatalities in shallow waters, while the mysterious deep-sea inhabitants successfully withstood the upheaval. This suggests that a supernova can affect our atmosphere and surface waters, but it does not impact the depths of the ocean. Supernovas emit an extraordinary deluge of cosmic rays into the universe. Upon hitting other atoms, they disintegrate, releasing a torrent of hazardous shrapnel referred to as muons. Envision charged particles similar to electrons, but possessing a mass 200 times greater. Captivating. They explore further and cause significant damage. They can permeate our atmosphere, invade our dermis, infiltrate cells, and modify our DNA. They will seamlessly traverse a mouse. Nevertheless, situate them within the anatomy of a more substantial organism. The impact on a creature as immense as a megalodon may be nothing less than remarkable. Muons possess the extraordinary ability to damage DNA, leading to mutations that may contribute to the development of cancer. Nonetheless, their considerable power wanes when navigating through water, potentially elucidating why only the mysterious deep-sea organisms have succeeded in surviving. The extinction serves as a poignant reminder of our interconnectedness with the cosmos and its ever-evolving mysteries. Is that not intriguing? Occasionally, a supernova erupts in a magnificent spectacle, accompanied by other intriguing cosmic events. Understood. It is a captivating exhibition. Negative. The impact on life on Earth and human existence is undoubtedly significant. Are we on the verge of extinction? Is Betelgeuse poised for a remarkable explosion? That is exhilarating. You have accurately identified the issue. We developed a gizmo that provides a thrilling experience across the cosmos. Commence a thrilling expedition across the cosmos. Ideas about space and time were not well defined in Aristotle's time, and they had not yet taken the forms we recognize today. Space was linked to the way things were spread out that were directly seen. Things that happened over time, on the other hand, were not directly seen, and it was hard to measure general time intervals. It was unclear how to define motion by combining space and time intervals, and it was challenging to distinguish motion from other types of change. But in reality, he didn't have a general formula or a straightforward way to measure speed, resistance, and force. He made a qualitative argument based on everyday experience, suggesting that effort is necessary to maintain motion, and the faster something moves, the more effort is required to keep it moving. Aristotle said, "A body will move through a given medium in a given time, and through the same distance in a thinner medium in a shorter time." He also said, "A body will move through air faster than through water, by so much as air is thinner and less corporeal than water." Based on this idea, it seemed logical to think that bodies of different weights fall through the air at various speeds. Additionally, if there were no resistance, a body would move from one place to another instantaneously, or at an infinite speed. The Aristotelians said that a vacuum can't exist in nature, because a body in a vacuum would not feel any resistance, and every force would make it move at an infinite speed. So solid, liquid, or gaseous things filled up space everywhere, giving it a lot of reality and slowing down the movements of moving things. The atomists, who later became known as Epicureans, posited that atoms can move freely through space at a constant speed. Aristotle said, "What can be the cause of their motion?" to counter the argument that atoms exist. The atomists claim that there is always movement, but they don't specify what it is or why it occurs, nor do they explain its cause. Later, René Descartes said something similar. A vacuum is against reason. Aristotle's common-sense law of motion remained in place until the Newtonian law of applied force emerged 2,000 years later, superseding it. Impetus, momentum. We shouldn't think that Galileo's genius alone made the big leap from Aristotle to Newton. Philoponus discussed impetus, now known as momentum, in the 6th century. It goes back to Hipparchus in the 2nd century BC. Robert Grosseteste and Roger Bacon were two scholars from the High and Late Middle Ages who developed the definitions we use today. Speed is the distance traveled in a given period, and acceleration is the change in speed over a given period. They said that bodies of different weights fall at the same rate. They used charts and diagrams to show what motion is like. William Heytesbury and other scholars at Merton College, Oxford, in the 14th century, showed that if v stands for speed at any given time, and a stands for a constant positive acceleration, their use of graphs to do maths was ahead of Newton and Gottfried Leibniz's discovery of calculus by 300 years. William Ockham, who also attended Merton College, stated that forces can act at a distance without bodies touching each other. Jean Buridan, a French philosopher who studied under Ockham and later taught Nicolas Oresme, believed that impetus was related to the speed at which a body was moving and the amount of matter it contained. We now refer to quantity of matter as mass and impetus or momentum as mv, where m stands for mass. Buridan said that the planets move on their own, within their orbits, because of their impetus. The force of a thrown stone keeps it moving, but air resistance slowly slows it down. Aristotelians didn't know what impetus was, so they believed that forces always pushed things that were in motion. They thought that the air that moved out of the way in front of a moving body flowed to the back, allowing it to move from behind and keep it moving. Buridan and his followers argued that bodies that fall straight down gain the same amount of momentum in the same amount of time, so they fall at the same rate. Leonardo da Vinci was a renowned Italian artist, scientist, and engineer who wrote extensively about various topics, including the rotation of the Earth, the origin and age of fossils, and the impossibility of perpetual motion. He proposed the idea that bodies fall at a constant rate, independent of their weight. In the late 16th century, Dutch-Belgian scientist Simon Stevin conducted experiments, and Galileo later gave him credit for his findings. He threw bodies of different weights off a tall building and saw that they all hit the ground at about the same time. In the early 1600s, French philosopher Pierre Gassendi dropped stones from the top of a ship's mast and demonstrated that the rocks always landed at the foot of the mast, even when the boat was in motion. Ptolemy said that if the Earth were to turn, a person who jumped would not land in the same place. This meant that if someone jumped off the deck of a moving ship, they wouldn't land in the same spot on the deck. Gassendi's tests proved that Ptolemy was wrong. Jeremiah Horrocks, a priest who died at the age of 22, demonstrated that the moon orbits the Earth in an elliptical path, a discovery that aligns with Kepler's laws. He said that the sun's light from far away was what caused the moon's motion to be disturbed. He considered the concept of universal gravity and observed that the planets alter each other's orbits. In his lectures and writings, Galileo Galilei synthesized, without giving credit, medieval discoveries about space, time, and motion. He demonstrated that free-moving bodies maintain their momentum, and balls rolling down inclined planes showed that bodies falling freely under the Earth's gravity experience a constant acceleration. He said that the length of a pendulum, not the weight of its bob, determines how long it will swing. He timed things by feeling his pulse or the flow of a water jet. Galileo was a big fan of the Copernican heliocentric system, but he didn't pay attention to Kepler's work or think about how planets move. He didn't know that a body moving in a circular orbit has a constant acceleration towards the center of the orbit. He thought that a planet moving in a heliocentric circular orbit did so naturally, without a force pulling it towards the sun. Giovanni Borelli, an Italian contemporary of Kepler, examined Kepler's work on planetary motion in light of Galileo's findings and considered the nature of the sun's gravity. The world system of Cartesian. Give me matter and motion, and I will build the universe. René Descartes, Discourse on the Method, 1637. At first, leaders of the Protestant Reformation were against Copernicus. "This fool," said Martin Luther, "wants to reverse the whole history of astronomy." But they later changed their minds. Science was safe in Reformation countries from the growing hostility of the Counter-Reformation. Rome held on to geocentrism for another 200 years, but countries in the northwestern part of Europe abandoned it, and soon they also abandoned heliocentrism. In the 17th century, two essential world systems emerged that modeled the universe mathematically and mechanically. René Descartes, 1596 to 1650. René Descartes, a famous French philosopher and mathematician, had a significant impact on all fields of study. He used the Aristotelian method of rightly conducting the reason and the Platonic principle that what is reasonable must be true to create a vast and sweeping system of natural philosophy that was more original than anything else since ancient times. The most important aspects were the mathematical concepts used in the physical sciences and the apparent dichotomy between body and mind. He clarified the nature of space, time, and motion, and developed laws of motion that were similar to Newton's laws, which emerged a few decades later. Descartes wrote in his Principles of Philosophy that only God can be infinite. He lived in Protestant Holland at the time, so he referred to the spatial extent of material things as indefinite instead of infinite, to reserve the term infinite for God alone. In the Aristotelian system, space ended at the sphere of fixed stars. In the Cartesian system, which Descartes developed, space extended indefinitely and was filled with stars and their planets. In the Aristotelian system, matter and ether filled every part of finite space. In the mechanistic Cartesian system, matter of different densities filled every part of space that could go on forever. Descartes thought that the mechanized world of matter and motion followed natural laws. He said, "We may well believe, without doing outrage to the miracle of creation, that by this means alone, all things that are purely material might in course of time have become such as we observe them to be at present." He also believed that all forces acted through direct contact, which meant that bodies had to be in physical contact with each other. It was unreasonable for forces to act at a distance without direct contact with matter, so it was impossible. This is similar to the etheric forces of medieval mysticism, elemental forces that acted as pressures and tensions, pushed and pulled, controlling all movements. In the Cartesian world system, the orbits of planets were attributed to the vortical movements of matter between planets, and gravity was understood as the pressure that swirling fluids exerted on objects. Descartes said that reason convinces us, and that space, being nothing, has no extension. How can nothing and space have length, width, and height? Only matter can extend, and space doesn't exist where there is nothing. There is matter of all kinds and densities everywhere in space. Descartes stated that the concept of a vacuum repugnant to reason does not exist anywhere. The concept of space, or the vacuum, was a pivotal idea in Cartesian science. This idea led Descartes to believe that the atomist theory was impossible. The principle of action by direct contact needed no gaps, continuous matter, and the ability to break things down into smaller and smaller pieces. If atoms exist, they would be separated by voids. How else could they be atoms? And since voids don't make sense, atoms can't exist. In his book Leviathan, Thomas Hobbes wrote, "For what is the heart but a spring, and the nerves but so many strings, and the joints but so many wheels giving motion to the whole body?" Hobbes was one of the first to highlight the shocking implications of the Cartesian separation of body and mind. The body, with its physical brain, was a part of the universe of matter and motion, and the mind was just a ghost that haunted the machinery of the body and brain. How can a mind that isn't made of matter control or affect a body that is? So, in clear-cut mechanistic terms, this is how the Cartesian duality of body and mind began. It remains an unsolved problem to this day. Christian Huygens, 22/9 tot 1990. Christian Huygens was a Dutch physicist and astronomer who played a pivotal role in the Cartesian scientific tradition and philosophy. He improved telescopes, he discovered the rings around Saturn, and is best known for inventing the pendulum clock. Before now, the accuracy of mechanical clocks on church towers was about the same as that of old candle and water clocks. Huygens's clocks with pendulums made scientific experiments and sailing much more accurate. Descartes was aware of motion that doesn't follow a straight line, which Galileo was not. Huygens showed that when something moves in a circle, it speeds up v² equals r towards the center of the circle, where v is the speed and r is the radius of the circle. The string pulls on the stone, causing it to spin faster and faster towards the hand. Huygens, like Descartes, thought that space was a part of matter and that gravity was a force that came from the pressure of vortices. The beginning of the age of reason. The Cartesians thought that the universe was infinite and that forces acting directly on things pushed and pulled them. Everything worked out for a reason, even though religious leaders steeped in biblical scripture and academics entrenched in ancient doctrine were strongly opposed to it. The liberating and exciting Cartesian philosophy spread quickly and captured the minds of free thinkers everywhere. The Cartesian system led to the Age of Reason, also known as the Enlightenment, in the 1700s. This was the time when the telescope, microscope, thermometer, barometer, and pendulum clock were all invented. Descartes began to doubt everything but the simple statement, "I think, therefore I am." It started the explosion of ideas in England that led to the creation of the Newtonian system. The Newtonian system of the world. I don't think of time, space, place, and motion as things that everyone knows. Principia by Isaac Newton, 1687. At first, English liberal theologians and philosophers viewed Descartes as a means of distancing themselves from medieval mysticism. However, his philosophy soon received more criticism than praise. Henry More, a theologian from Cambridge, was first impressed by the idea of a universe governed by natural laws. However, he later became horrified by the implications of Cartesian materialism and returned to the medieval notion that space exists independently because a spirit is present everywhere. More liked the idea, which many of his co-workers also enjoyed, of a finite, stoic universe of stars surrounded by an infinite, mysterious void. This is also how Isaac Newton saw the universe. Robert Hooke lived from 1635 to 1703. Robert Hooke, Christopher Wren, and Edmund Halley discussed concepts that Newton later explained in mathematical terms. Descartes stated that a body that can move freely will continue to move in a straight line at a constant speed as long as it is not acted upon to change its state. The sun's gravity must always be pulling on the planets because they don't move in straight lines. Instead, they move in curved orbits around the sun. Hooke used a conical pendulum to illustrate the concept and stated that mechanical principles can explain the motion of planets. Around the time that Newton was quietly thinking about these things, Hooke, a scientific genius, Edward Andrade calls him perhaps the most inventive man who ever lived, figured out that the force that pulls the planets to the sun and the moon to the earth is the same one that makes apples fall from trees. Hooke wrote, "I will explain. A system of e-world, differing in many particulars from any yet known, answering in all things to the common rules of mechanical motions. That all celestial bodies whatsoever have an attraction or gravitating power to their centers, whereby they attract not only their parts, and keep them from flying from them, as we may observe the earth does, but that they do also attract all other celestial bodies that are within the sphere of their activity. The gravity that, in Pythagoras, is spherical." Isaac Newton, one of the most famous scientists of all time, synthesized the ideas of many thinkers from the Middle Ages. He developed the dynamic theories of motion and universal gravity, and built a system that gave science the power and beauty it had always sought. In an unpublished manuscript called De Gravitation, which he wrote while at Cambridge, Newton stated that an infinite and eternal divine power fills all space and extends infinitely in all directions. Descartes said that there is no space where there is no matter, but Newton said that there is no space where there is no matter. Instead, spirit alone gives space its extension. If you say that space can't exist without matter, you're saying that spirit and God can't exist in the universe. During his lifetime, Newton's ideas about what space is like mainly remained unchanged. Descartes noted that matter extends infinitely, but Newton argued that God created a finite material system within an infinite space. The theologian Richard Bentley's questions significantly altered Newton's concept of a finite cosmos of stars, a Stoic notion, 25 years after it was first proposed. At the age of 27, Newton became the Lucasian Professor of Mathematics at Cambridge University. He left the job in 1701, 32 years later, when he became Master of the Mint. He was single his whole life, just like Descartes. Most biographers have not talked about Newton's scientific work or the fact that he spent many years studying alchemy and the Bible. Hooke's broad perspective marked the emergence of the Newtonian mathematical universe. Newton was a brilliant thinker who spent many years thinking about the natural philosophy of space, time, and motion. He turned all of the previous graphical descriptions into mathematical prescriptions. Newton wrote in his book, Mathematical Principles of Natural Philosophy, also known as Principia, that space is absolute space in its nature, without relation to anything external, remains always similar and immovable. He also wrote that absolute, true and mathematical time of itself and from its nature flows equably without relation to anything external. We understand what Newton meant by absolute space, but not what he meant by absolute time. What does the flow of time mean? The three laws of motion that Newton made are: 1. A body stays at rest or moves in a straight line until an outside force makes it change that state. We should remember that velocity has both speed and direction, and a body's momentum, which is a measure of its velocity, stays the same unless an outside force acts on it. 2. The rate at which momentum changes over time is equal to the force applied and points in the same direction. If the mass stays the same, the rate of change of momentum is the same as the rate of change of velocity, and the law of motion becomes applied force equals 1/4 mass times acceleration. The force is in the direction of acceleration. 3. There is always an equal and opposite force acting on every force at the same time and place. This critical law says that the total of all forces at any given point is 0. An equal and opposite force pushing up on the ground, for example, changes a person's weight. The third law gives rise to the idea of inertial force. So, the total amount of forces acting on a body that can move freely is 0. The inertial force is the force that occurs when an object speeds up and acts in the opposite direction of the acceleration. When something moves in a circle, its acceleration is towards the center, but the inertial force, in this case, the centrifugal force, is directed away from it. A stone spinning at the end of a string experiences a centrifugal force that pulls it outward, which is equal and opposite to the tension in the string, pulling it inward. The third law explains why astronauts in a spaceship orbiting the Earth don't feel the pull of the Earth's gravity. The spacecraft's inertial force cancels out the Earth's gravitational force. The remarkable aspect of the Newtonian laws is that when a body moves freely, it follows a path where the inertial force cancels out the gravitational force, and the body experiences no net force. Because the Earth orbits the Sun, we can't feel the Sun's pull on us. According to Einstein, the principle of equivalence is crucial for developing the theory of general relativity, which states that bodies that move freely follow paths as if gravity doesn't exist. So, when someone is in free fall, like an astronaut in a spaceship, they don't feel any gravitational force. But watch out for tidal forces. Relative and absolute movement. In the world of Newton, motion is both relative and absolute. We don't feel any inertial force when a car's speed remains constant. We constantly check its speed compared to other vehicles or stationary objects on the side of the road. There is no inertial force as long as the relative speed stays the same. A passenger who is blind or deaf can't tell what the car is for. There is no absolute value for the speed. It is only relative. However, when the speed changes, a force called the inertial force is felt, which we experience when we accelerate. This force is not caused by moving relative to anything. In the Newtonian system, acceleration is a change in speed, direction, or both. The passenger, with their eyes closed, guesses the acceleration based on the size and direction of the inertial force they feel. The inertial force goes forward if speed goes down, or backward if speed goes up, when speed changes. When the direction changes but nothing else does, the inertial force goes to the left when turning to the right, or to the right when turning to the left. In Newtonian space, uniform velocities are relative and measured against one another, while changes in velocity, accelerations, are absolute and measured against nothing. In modern relativity physics, the same principle applies. Acceleration is absolute, while uniform velocity is relative. The force of gravity between two objects changes as the distance between them changes. The force that pulls a planet towards the Sun changes as the planet gets farther away from the Sun. How did Kepler find this out? The third law of Kepler is the answer, see page 107 for Kepler's laws. Kepler's planet moves in a circle around the Sun, with a radius of r and a speed of v. Huygens shows that the acceleration towards the center of the orbit is v squared equals r. This means that the inertial force that pushes the planet away from the center is mass acceleration, or mv squared equals r, where m is the planet's mass. The Sun's gravity must be equal and opposite to the centrifugal force that the Earth feels. Newton showed that a spherical object attracts other objects as if all its mass were concentrated at its center. He also revealed that the orbits of planets are ellipses, and the orbits of all objects that can move freely in the Sun's gravitational field are either ellipses, parabolas, or hyperbolas. In Newton's world, all objects pull on each other with gravitational forces that are proportional to their masses and the square of the distance between them. Isaac Newton was a maths professor at Cambridge University and gave 8 lectures a year, but not many students came. He wrote his great work, The Mathematical Principles of Natural Philosophy, in less than 2 years. Halley pushed him to publish it in 1687, and it sold for 7 shillings a set. Newton used a few definitions and axioms and a lot of propositions to explain mathematically the tides on Earth that happen twice a day because of the Sun and Moon, the flattening of the Earth at the poles because of its daily rotation, the axis of the Earth's rotation changing every 26,000 years because of the Earth's equatorial bulge, the Moon's orbit changing, and the paths of the planets and comets. He and Gottfried Wilhelm Leibniz, a German philosopher and mathematician, both independently developed the ideas that led to the creation of calculus. Robert Boyle left money in his will to fund an annual lecture series that would combat the atheism that was often discussed in coffeehouses and taverns. Robert Boyle chose the learnt clergyman Richard Bentley to give the first set of lectures in 1692. In his last 2 lectures, A Confutation of Atheism from the Origin and Frame of the World, he demonstrated how the wonders of the Newtonian system proved, beyond a doubt, that there is a divine power. He said that the laws of nature alone couldn't explain the wonders of the natural world, and that they needed to be backed up by acts of divine power. Before publishing his lectures, Bentley consulted with Newton about a few technical issues. His profound and troubling questions prompted Newton to re-evaluate his ideas about the universe. Newton's 4 letters to Bentley are some of the most critical documents in the history of cosmology. First letter, December 10th, 1692. In the first letter, Newton answered Bentley's question about how gravity works in a finite system of stars. He said that a universe made up of self-gravitating matter must be unbounded. Otherwise, all matter would fall to the middle of the whole space, and there compose one great spherical mass. But if the matter were evenly spread through infinite space, it would never form one mass, but rather an endless number of great masses scattered throughout all of infinite space. Such an arrangement. Second letter, January 17th, 1693. In his second letter, Newton said, "You argue that every particle of matter in an infinite space has an infinite quantity of matter on all sides, and by consequence, an infinite attraction every way, and therefore must rest in equilibrium, because all infinities are equal." Newton had fully agreed with Bentley that gravity meant Providence had created a universe of enormous precision. It's hard to believe that all the particles in infinite space are so perfectly aligned. The job is as hard as making just one needle, but there are an endless number of them, as many as there are particles in an infinite space, standing perfectly still on their points. But it is possible, at least by a divine power. If they were put in that position, I agree with you that they would stay there forever without moving, unless the same power that put them there moved them. So when I said that matter that is not perfectly balanced or at rest would come together by its gravity into one or more big masses, I meant matter that is not perfectly balanced or at rest. So gravity might be what makes the planets move. Still, it could never make them move in such a way around the sun without divine power. For this and other reasons, an intelligent agent made the system's frame. The third letter, dated February 11th, 1693. I had thought very little about the idea of using mechanical principles to create the frame of the world from matter evenly spread through the heavens. But your letters made me think about it more, so I am writing to you again to tell you more about it. Newton provided further details about earlier arguments that a divine power was necessary to create the initial conditions. Fourth letter, February 25th, 1693. Newton told Bentley again that his mechanistic view of the world didn't mean that there was no need for a divine power to sustain it. This frame of things could not always exist without a divine power to preserve it. Gravity for everyone. The Newtonian theory of universal gravity, in which all bodies attract one another, reinforced the growing belief that the universe must be edgeless and, therefore, according to Euclidean geometry, infinite. A finite universe bounded by a cosmic edge would have a center of gravity, and the attraction between its parts, said Newton, would cause them to fall into the middle of the whole space, and there would be one great spherical mass. This argument caused him to abandon a finite Stoic cosmos in favor of an infinite Epicurean universe. In an infinite uniform universe, no preferred direction exists where gravity can pull and cause matter to fall into a single middle. In the second edition of the Principia, published after the Bentley letters, Newton wrote, "The fixed stars, being equally spread out in all points of the heavens, cancel their mutual pulls by opposite attractions. Each particle of matter, pulled equally in all directions, remains in equilibrium. But an unstable equilibrium, as Bentley pointed out. The theory of universal gravity supported the belief that the universe is static on a cosmic scale, and initiated the idea that on more minor scales, gravity causes matter to condense and form astronomical bodies, such as stars and planets. Theory of atoms. Atomism, an inspired theory, did not enter the mainstream of science until the 17th century. Pierre Gassendi, a 17th century French natural philosopher, revived the atomist theory despite lingering Aristotelian objections and its association with Epicurean philosophy, which was often linked to atheism. The theory played a prominent role in the thinking of men like Robert Boyle, Otto von Guericke, Mayor of Magdeburg, and Newton. In his book Optics, Newton wrote, "It seems probable to me that God in the beginning formed matter in solid, massy, hard, impenetrable particles, of such size and figures, and with such other properties, in such proportions to space, as most conduced to the end for which he formed them, even so very hard as never to wear or break in pieces." Newton interwove the old atheistic atomic philosophy into the contemporary religious doctrine and triumphed by compromise. He wrote prophetic words, "There are four agents in nature, able to make the particles of bodies stick together with extreme attractions, and it is the job of experimental philosophy to discover them. We now have high-energy particle accelerators capable of doing this." 3 world systems from classical antiquity survived and became the foundations of European natural philosophy in the 16th and 17th centuries. The Aristotelian system of geocentric celestial spheres had planetary orbits inside a sphere of fixed stars. Medieval editions filled the heavenly spheres with angelic beings and surrounded the sphere of fixed stars with the empyrean, where God was believed to reside. This was the official view of the universe in Judaism, Christianity, and Islam. The Epicurean system posited an infinite void filled with an endless number of uniformly distributed worlds composed of atoms and governed by natural laws. Descartes changed this system by adding matter and denying the existence of atoms. After writing to Bentley, Newton modified this system by incorporating spirit while preserving its atomicity. In the 4th century BC, the Athenian playwright Aristophanes said, "Whirl is king." Whirlwinds and whirlpools were significant in mythology, and early scientific theories primarily focused on vortex scenarios. Many philosopher-scientists thought that a primordial vortex formed the planets and stars. The idea of swirling fluids in large and small vortices was at the heart of the Cartesian system. Newton's proof that gravity and the laws of motion explain planetary orbits led to the eventual abandonment of the Cartesian vortex theory. Immanuel Kant and Pierre-Simon Laplace proposed the idea of swirling matter into the solar nebula hypothesis. To this day, whirl is the king of our cosmogonic theories of star and galaxy formation. Gottfried Leibniz, 1646 to 1716, wrote a letter to Samuel Clerk, saying that space is not an absolute reality and that there is no space without matter. Clerk argued in favor of Newton's ideas and the existence of an absolute space that is separate from matter. Leibniz shared the Cartesian belief of many continental philosophers that space is meaningless. He also shared the Cartesian belief that forces could not act at a distance unless a material medium carried them. The universal gravitational constant, which is now called G, doesn't come in units that measure masses in solar masses. For example, Kepler's third law says that p squared equals r cubed, where p is the period and r is the radius of an orbit. Distances are measured in astronomical units, the distance from the Sun to the Earth, and time intervals are measured in years. 5 Lucretius said in Book 1 of De Rerum Natura that space is infinite and has no limits. He said, "If all the space in the whole universe were closed in on all sides with fixed boundaries, then all matter, because of its weight, would have flowed together from all sides and sunk to the bottom. There would be no sky or sunlight, and nothing could move under the canopy of the sky. All matter would be still, piled up for an infinite amount of time. However, the universe has never had a break like that, because everything is always in motion." Lucretius's argument was similar to Newton's reasons for believing in infinite space. He used the idea of ceaseless movement to vaguely understand what Newton and Bentley did not discuss: the possibility of a finite system of moving stars in stable equilibrium, as in a galaxy. They both agreed that stars stretch away endlessly, as in the Epicurean universe, and believed, on the other hand, that if the material system were finite, as in the Stoic universe, the stars would fall into the middle. It depends on how the mass is distributed within the cluster. For a cluster with uniform density, A3 equals 5. Stars move in different orbits around the cluster's center of mass and don't have to fall into the middle, as Newton thought. The Victorian one-island universe, a single giant galaxy in an infinite vacuum, obeyed the virial theorem. In 1726, Voltaire fled France for England for 3 years to get away from his enemies, who were the victims of his sharp wit. His published Letters from London on the English has comments that compare the Cartesian and Newtonian systems. "A Frenchman coming to London," Voltaire wrote, "finds things very different in philosophy and everything else. He left the world whole, but here he finds it empty. In Paris, you can see the universe made up of swirling bits of matter. In London, you can't see any of this. The moon's gravitational pull on the sea causes the tides to change, but for the English, the sea appears to pull towards the moon. The sun, which has nothing to do with the matter in France, has to contribute almost a quarter of the time. With your Cartesians, everything happens because of pressure, which is hard to understand. With Monsieur Newton, it occurs due to attraction, which is also challenging to comprehend. 7. Determining the distances to stars is not easy. A Dutch astronomer, Christian Huygens, used a crude photometric method in the late 17th century. He assumed that all stars are similar to the sun. He observed the sun in a dark room through a small hole in a screen covering the window. By adjusting the size of this hole until its brightness matched that of Sirius at night, he estimated Sirius to be 30,000 astronomical units away, or roughly 0.5 light years. This method relies on judging the brightness of Sirius during the daytime to estimate its nighttime brightness. The young Scottish astronomer James Gregory, unknown to Huygens, had proposed a photometric method several years prior that did not depend on memory. Gregory assumed that the nearby bright stars were sun-like and compared their brilliance with that of the outer planets, Mars, Jupiter, and Saturn. Knowing the sizes of the planets and their distances from the Sun and Earth, and taking into account the imperfect reflection of sunlight from their surfaces, he estimated the distance of the nearest stars to be several hundred astronomical units. Isaac Newton referred to Gregory's method in his System of the World, and, in unpublished work, placed the brightest stars at 500,000 astronomical units, or roughly 8 light-years. This estimate was a remarkable anticipation of more recent measurements. 8. This most beautiful system of the sun, planets, and comets could only come from the advice and control of an intelligent and strong being. And what if the fixed stars are the centers of other systems like them, which were made by wise and informed advice? In that case, one person must be in charge of all of them. Isaac Newton, Principia, 2nd edition, translated by Andrew Mott, pages 389 to 390. Where does nature get the idea that everything is in order and beautiful? Isaac Newton, Optics. People, Revoice is an excellent addition to the human race. The words are on Newton's tomb in Westminster Abbey. After Newton, progress in astronomy was initially slow. Better telescopes had not yet been made, and photography and spectroscopy were new to the field. Scientists have also determined the chemical compositions and radial velocities of stars and nebulae. They also figured out how to tell the difference between nebulae in the galaxy and those outside of it, how to find and calibrate distance indicators, how to identify globular clusters as systems of stars in and on the edges of the galaxy, universes with hierarchies. People who live in deserts, sail the seas, or reside far from city lights understand why the night sky was so crucial to people in the past. On clear moonless nights, the sky is full of bright stars and hazy lights, and the Milky Way, or Via Lactea, stretches across the sky like a ghost. At the start of the 18th century, the Cartesian and Newtonian systems, which had no edges or centers, were adorned with stars. But as astronomers learnt more and got better telescopes, it became clear that stars are not evenly spread out across the sky. Thomas Wright of Durham introduced new ideas about the Milky Way, which he outlined in his book, An Original Theory of the Universe, published in 1750. At first, he thought that the stars were promiscuously distributed through the mundane space. But later, because of the Milky Way, he realized that the stars were scattered in some regular order. A feature of Wright's universe was the existence of a supernatural galactic center. At this center of creation, he would willingly introduce a primitive fountain, perpetually overflowing with divine grace, from whence all the laws of nature have their origin. He proposed two possible constructions of the Milky Way system: either a ring-shaped distribution of stars encircling the center of the Milky Way, similar to the rings encircling Saturn, or a spherical shell of stars, concentric with the center, in which the Milky Way consists of the stars seen in a plane, tangential to the shell. Wright went even further and considered the possibility of multiple centers of creation. The distant nebulae, which appear as faint fuzzy lights in the sky, could be other creations or abodes of the blessed, much like our Milky Way. The endless immensity is a limitless plenum of creations that are not unlike the known universe. Kant, a German philosopher and scientist, reviewed Wright's work and adopted the idea that the Milky Way is a disc-shaped or lens-shaped distribution of stars, and that distant, similar Milky Way systems surround the Milky Way. In his theory of the heavens, Kant presented a scientific account of Wright's views in 1755. The stars of the Milky Way form a rotating disk held together by gravity, said Kant, and the fuzzy nebulae are similar rotating Milky Way systems. It is natural to assume that these nebulae are systems of numerous suns, which appear because of their stance, crowded into a space so limited as to give a pale and uniform light. Their shape, which is just what it should be according to our theory, their light, which is very faint and shows that they are very far away, and their similarity to our system of stars all point to the fact that these elliptical spots are systems of the same order as our own. Kant said that these Milky Ways, now called galaxies, are probably clustered together to form huge systems of many galaxies. He also stated that these vast systems are clustered together to create even larger systems, which are then clustered together to form even larger systems, and so on, throughout infinite space. In such a cosmic hierarchy, each level consists of an endless array of centers, and the centers at each level form clusters around the centers of the next higher level. At the highest level of infinite order, the ultimate center dominated the universe's structure. We can observe the emergence of the first members of a progressive relationship between worlds and systems. The first part of this infinite progression allows us to infer what must be true about the whole. There is no end here, just an endless abyss where all of human thought's power sinks into nothingness. Johann Lambert, a Swiss-German mathematician, had similar thoughts. The main difference was that Lambert believed each center was home to a body he referred to as a dark regent. In Cosmological Letters, Lambert wrote in 1761, "The eye, assisted by the telescope, may at length penetrate to the centers of the Milky Way, and why not even to the center of the universe?" In 1855, von Humboldt, a restless man with a wide range of scientific interests, wrote in his book Cosmos, "Our cosmical island forms a lens-shaped system of stars." Soon after, authors began to call cosmical islands island universes and island universes. However, it can be unclear when galaxies are referred to as universes. Instead, we will call galaxies islands. Thus, a Stoic-like system is a one-island universe, and an Epicurean-like system is a many-island universe. Benoit Mandelbrot, a French mathematician, coined the term fractal to describe a hierarchy that repeats itself at different scales or levels. For instance, the irregularities of a coastline may look the same when viewed from a distance of tens of meters, then kilometers, and finally hundreds of kilometers. Kant's hierarchy had fractal properties. At the first level, stars form clusters of N1 stars. At the second level, star clusters form galaxies of N2 star clusters. At the third level, galaxies form galaxy clusters of N3 galaxies. At the fourth level, galaxy clusters form superclusters of N4 galaxy clusters, and so on. The Nebula Hypothesis. Pierre-Simon de Laplace, 1749 to 1827, a French mathematician and astronomer, demonstrated in his book Celestial Mechanics that the planetary system was tabijim. This meant that there was no need for a divine power to make periodic corrections, as Newton had said. In his non-mathematical and popular book System of the World, first published in 1796, Laplace discussed the idea that the solar system formed from a rotating and contracting cloud of gas. This idea is now accepted in a more modern form. The hypothesis of the Kant-Laplacian nebula. Astronomers and natural philosophers were fascinated by nebulae, which means cloud. In the 1800s, every fuzzy patch of light in the night sky was thought to be a possible interstellar cloud of condensing gas. Even the Andromeda Nebula, a vast galaxy next door, and other similar nebulae were considered to be forming solar systems. Cosmical islands, the nebulae far away. The small, faint and fuzzy patches of light and the density decrease with size as L to the power of -1 to the power of 11. Suppose that 1,000 galaxies, each of size 1 in the night sky, according to the right Kantian interpretation, were distant Milky Way systems of stars, and according to the Kant-Laplacian interpretation, were clouds of gas condensing into solar systems. The Milky Way interpretation favored a many-island universe, whereas the solar system interpretation favored a single-island universe. William Herschel, 1738 to 1822. Herschel, a professional musician from Germany, relocated to England at the age of 19. His sister Caroline later joined him, and they both became very interested in astronomy. They used the latest telescopes to break up many nebulae into groups of stars. William became famous after he discovered a seventh planet beyond Saturn, which was later named Uranus. He was known as the best astronomer of the 18th century. The Herschels used telescopes that were unmatched in their ability to gather light and see the stars. William wrote about their findings in publications based on three ideas. I. Starlight can pass through interstellar space. I. Every star is like the sun. Badesa Shi. Stars are spread out evenly throughout space. All three were later found to be an error. The first and second assumptions meant the faintest stars were the farthest, and apparent brightness could be used as a distance measure. The first and third assumptions meant the Milky Way extended the farthest, where the sky appeared the most crowded with stars. Based on these assumptions, the Herschels charted the heavens and found the Milky Way to be a flattened system, with the Sun positioned near the center. The galactocentric theory that the Sun is at the center of the galaxy came about primarily because of assumption I. At the time, no astronomer knew that clouds of dusty gas drifting between the stars absorbed starlight. The constellation of Sagittarius, which hides the galaxy from view, is at the center of the galaxy. William thought that the starless areas of the sky, which are now known to be caused by clouds of gas and dust blocking our view, were holes in the sky, through which we see the Herschels showed that the motions of double stars, two stars in orbit around each other, follow Kepler's laws. In 1785, William wrote a paper titled On the Construction of the Heavens, which suggested that many nebulae might be very distant systems, similar to our Milky Way. for which reason they may also be called Milky Ways by way of distinction. In a letter, he said he had discovered 1,500 universes, whole sidereal systems, some of which might well outvie our Milky Way in grandeur. For most of his life, he supported the view that the universe is endlessly populated with galaxies, much like the Milky Way. However, the riddle of the nebulae grew more puzzling, and with the rise in popularity of the Kant-Laplacian nebula hypothesis, William grew less confident and eventually expressed the opinion that possibly most nebulae existed within the Milky Way. He learned from observing double stars that stars can vary significantly in brightness, which made the second assumption, that all stars are alike, impossible. The third assumption, that stars are evenly spread out in space, was also wrong, and he realized that stars are scattered in a very irregular way. Some regions of space, such as those in Orion, appeared to be a shining fluid rather than a group of stars, which led him to question the initial assumption. William Herschel thought that living things lived on the moon and planets. However, it seems strange that the most famous astronomer of the Age of Reason thought that there was a cool surface with living things on it under the bright atmosphere of the sun. This was before physics and astronomy came together, and the new field of astronomy was born. The new astronomy. The speed of light. Descartes was sure that light travels at an infinite speed, and that we see the world as it is. If the light rays that made up an image came from different distances and times, our reconstruction of the outside world would be very confusing. A finite speed meant that an object, at the moment of observation, was not what it seemed. It had moved and altered its appearance. Objects at greater or lesser distances would have moved and changed by greater or lesser amounts. The idea that when we look out into space we look back in time seemed too incredible to Descartes and many other Cartesians. But in 1676, the Danish astronomer Ole Rømer announced at the Paris Academy of Sciences meeting that the eclipse of Io, a moon of Jupiter, on November 9th would occur 10 minutes late. His prediction was based on earlier records. Rømer explained that the Earth was moving away from Jupiter, and the delay would be caused by the extra distance that light had to travel to catch up with the Earth. This correct prediction established him as the discoverer of the finite speed of light. The results, updated by Edmund Halley, showed that light travels at the enormous speed of 300,000 kilometers a second and takes only 500 seconds to travel a Sun-Earth distance, known as an astronomical unit. In a paper called Concerning the Distance of the Fixed Stars, Francis Roberts said in 1694 that the stars were farther away than a certain minimum distance because the Earth's orbit around the Sun had not yet been detected. He also said that light takes up more time traveling from the stars to us than we do in making a West India voyage, which is usually done in 6 weeks. This was the first time light travel time was used as a distance measure in cosmology. However, the parallax of even the closest stars is much less than Roberts thought, and their light takes years, not weeks, to reach us. James Bradley's discovery of the aberration of light in 1729 put an end to the debate over the finite speed of light. He observed that the stars appear to move back and forth by a slight angle during the year because the Earth orbits the Sun. This angular displacement, which was not affected by the distance of the stars, unlike parallax, agreed with Rømer's finite speed of light. When a person walks in rain that falls vertically, the rain slants towards their face, and the umbrella is tilted forward. The slant of the rain is like the aberration of light. Agnes Clerk, a well-known historian of astronomy from the 1800s, wrote in her book System of the Stars, 1890, for our view of sidereal objects is not simultaneous. Using light to communicate with them takes time and occurs after the sensible impressions of their location, based on how far away they are. We see the stars not where they are, not even where they were at any one instant, but on a sliding scale of instants. A significant fact in cosmology is that when we look out into space, we also look back in time. And the farther we look out into space, the farther we look back in time. Light beams. Newton discussed ether waves that move like sound waves or waves on the surface of water, but he still believed that light is composed of particles. He asked, "Aren't the rays of light tiny bodies emitted from shining bodies?" Robert Hooke and Christian Huygens came up with wave theories of light that explained reflection and refraction, the bending of light as it passes through a prism. A century later, in the early years of the 19th century, Thomas Young, a physician, scientist, and authority on Egyptian hieroglyphics, showed how the wave theory explained interference. Superposed waves of the same wavelength add and subtract, and diffraction, deflection according to the wavelength of waves passing through an aperture. In the middle decades of the century, Michael Faraday, an outstanding experimental physicist, and James Clerk Maxwell, an outstanding theoretical physicist, explored and unified electricity, magnetism, and the properties of light, developing the modern theory of electromagnetism. Early in the 20th century, Max Planck and Albert Einstein demonstrated that light exhibits both wave-like and corpuscular properties, and radiation particles are now referred to as photons. William Huggins, 1824 to 1910. The new astronomy of the 19th century, which is now called astrophysics, began when astronomers used physics to study stars and nebulae. The laboratory was moved to the observatory. William Huggins was a major contributor to the new science. He was the first to utilize the latest technologies, such as photography and spectroscopy, in astronomy. His wife, Margaret, helped him a lot later on. Spectroscopic analysis of sunlight had already shown that the sun was composed of the same elements as the Earth, and Huggins decided to apply the same method to the stars. For most of the 1800s, astronomers had a big problem figuring out what the nebulae were, those fuzzy patches of light in the night sky. They had three options. The nebulae were: A. Galaxies that are far away from us, like our own. B. Clouds of gas that are swirling around and forming stars and planets. C. Groups of stars that haven't been resolved yet in and around the galaxy. The first option, A, was the right-Kantian many-island universe, which is less popular now that William Herschel is no longer supporting it. The second option, B, was the Kant-Laplacian nebula hypothesis, which is gaining popularity. The third option was that many nebulae were clusters of stars that had not yet been resolved, a concept that is gaining popularity due to the discoveries made by much more advanced telescopes. A one-island universe was possible with options B and C. A light spectrum from a luminous source shows how the intensity varies with wavelength. A spectrum often displays bright and dark narrow regions called spectral lines. These are the emission, glowing, and absorption, dark, lines at different wavelengths that identify the emitting and absorbing atomic elements. Working in his home observatory, Huggins compared the spectra of light from stars, nebulae, and comets with the spectra of elements excited in spark gap discharges. In 1863, Huggins finally succeeded and announced to the scientific world the news: the heavens are composed of the same elements as the sun and earth. This was the death blow to many old beliefs, and ordinary people began to turn from the churches to the observatories for knowledge on the nature of the starry heavens. In 1864, a year later, William Huggins wrote, I directed the telescope for the first time to a planetary nebula in Draco, and then, with some hesitation, put my eye to the spectroscope. Wasn't I about to see a secret place where things were made? What he saw wasn't what he thought. The spectroscope didn't show the continuous spectrum of a hot star. Instead, it showed a spectrum of lines that are typical of an excited gas. The mystery of the nebulae was solved. The answer, which came to us in the light itself, read, "Not an aggregation of stars, but a luminous gas." This discovery put to rest all doubts about the truth of the Kunt-Laplacian nebula hypothesis. The puzzling elliptical and spiral nebulae were not clusters of suns, as many had previously thought, but gaseous nebulae that were getting smaller as they lost heat, forming solar systems. Thus, assumption A, the Wright-Kunt hypothesis, was dead. The Doppler effect. Huggins was also the first to measure the radial velocity, the speed at which stars move away from and towards us, by looking at how their spectral lines changed. The French scientist Armand Fizeau predicted and calculated this change in 1848. Fizeau was also the first person to measure the speed of light using methods on Earth in 1849. When a light source, like a candle or a star, moves away from an observer, all of its radiation wavelengths get longer, and all of its frequencies get shorter. When the source moves towards the observer, all of its wavelengths get shorter, and all of its frequencies get longer. Huggins wrote in The New Astronomy, a Personal Retrospect, "To a swimmer striking out from the shore, each wave is shorter, and the number of waves he goes through in a given time is greater than would be the case if he stood still in the water." Christian Doppler, an Austrian physicist, showed in 1842 that a receding or approaching sound source is heard with a lower or higher pitch than when stationary. In 1848, he suggested that stars have different colors due to their motions, and that stars in binary systems periodically change their color, becoming blue when approaching and red when receding. Fizeau made the correct calculation and showed this was not the case. The displacement of spectral lines caused by relative motion was known in the 19th century as the Fizeau-Doppler effect, and today, perhaps less justly, as the Doppler effect. Detection of the effect was difficult until photography advanced to the stage where dry and sensitive plates could be exposed for hours in clock-driven telescopes. William Huggins prophetically wrote of the Fizeau-Doppler effect in 1868 that it would be scarcely possible to sketch even in broad outline the many glorious achievements that doubtless lie before this method of research in the immediate future. An atomic theory that works. John Dalton's book, New System of Chemical Philosophy, published in 1803, laid the groundwork for the modern atomic theory of matter. It was an immediate success. Dalton was the first scientist to make the nuclear theory quantitative and to introduce the Greek word atom into the field of chemistry. He demonstrated that matter is composed of atoms of varying weights by showing that elements combine in specific proportions by weight to form chemical compounds. For example, hydrogen had an atomic weight of 1, carbon had an atomic weight of 12, oxygen had an atomic weight of 16, and so on. In 1897, Joseph Thomson found the negatively charged electron. In 1911, Ernest Rutherford discovered the positively charged atomic nucleus. In 1913, Niels Bohr developed a mechanical model of the atom, which featured electrons orbiting the nucleus. A few years later, Erwin Schrödinger, Werner Heisenberg, and other physicists used quantum mechanics to create the modern wave mechanical model of the atom. Bohr said, "When it comes to atoms, language can be used only as in poetry." The 19th century standard cosmological model. The Victorian universe was the standard model of the 19th century during the reign, 1837 to 1901, of Queen Victoria of Great Britain. Propelled by the rise of new astronomy, it reached its final form towards the end of the century. It was a one-island universe. Providentially, the Earth and Sun were located at the center of the galaxy, the universe's mainland, surrounded by small islands. The galaxy, Figure 4.12 consisted of approximately 1 billion stars, numerous clusters of stars, often unresolved and on the outskirts, and gaseous nebulae, mostly condensing solar systems and planetary nebulae. And beyond, the galaxy stretched an endless mysterious void, more fit for contemplation by theologians than astronomers. The many wonders of the Victorian universe, glorified in hundreds of popular astronomy books and proclaimed from every pulpit, thrilled a large audience in Europe and North America. In her 1890 book, The System of the Stars, Agnes Clerk, a renowned historian of astronomy from the late 1800s, summarized the prevailing views of the time. She said that some nebulae were clouds of swirling gas, and others were groups of stars that couldn't be resolved, but none were galaxies like our own Milky Way. No reasonable person can continue to believe that any one nebula is a star system of the same rank as the Milky Way. It is almost sure that everything in the sphere, including stars and nebulae, belongs to one huge group and is arranged in an orderly way within the limits of one all-encompassing plan. This plan is all-encompassing, at least as far as we can know. Science doesn't care about the infinite possibilities beyond that. This was the standard model of the Victorian universe, which was passed down to the 20th century. In some ways, the Victorian universe was the old Stoic one-island universe, but with stars, planets, and gaseous nebulae composed of atoms similar to those in the solar system. The Stoic solution to the riddle of the night sky made the one-island universe even more likely. Clarke wrote, "It is almost certain that the stellar system has measurable dimensions. If it didn't, darkness would be gone from our skies, and the intense inane glowing with the mingled beams of suns that are impossible to tell apart would confuse our weak senses with its dull beauty. In an infinite universe full of stars, every line of sight from the eye must eventually hit the surface of a star. This means that stars must cover the whole sky. This is why Olbers's paradox asks, why is the sky dark at night? However, Clarke's idea of a finite cosmos of stars is only one of many possible answers, and it wasn't the one that was accepted 100 years later. The age issue, Jews, Christians, and Muslims all thought the universe was only a few thousand years old until the 18th century. However, new evidence from geology and paleontology, the study of fossils, shows that it is much older, which puts religious texts at odds with science. The doctrines of compromise were created to explain that natural and supernatural laws had alternated in their control of the earth, and that disasters, such as life-destroying floods, had occurred on Earth at regular intervals, long ago and far away. For more than 200 years after Romer's discovery, astronomers largely ignored the impact of the finite speed of light on the universe's age. There were a few exceptions. William Herschel, who was bolder than most, sometimes said that we see the heavens as they were long ago. In 1702 he wrote, "A telescope with a power of penetrating space, like my 40-foot one, has also, as it may be called, a power of penetrating time past." The light rays from a particular very remote nebula must have been almost 2 million years on their way, and consequently, so many years ago, this object must already have had an existence in the sidereal heavens to send out those rays by which we now perceive it. William Herschel's son, John, a more cautious man, wrote in 1830 in a treatise of astronomy, "Among the countless multitude of such stars visible in telescopes, there must be many whose light has taken at least 1,000 years to reach us. And that when we observe their places and note their changes, we are reading only their history of 1,000 years, anterior date, wonderfully recorded. John Herschel, a pillar of Victorian society, was not a Don Quixote to sally forth and tilt at solidly held religious beliefs concerning the universe's age. But not von Humboldt, who wrote in his book Cosmos, "It remains more than probable, from the knowledge that we possess of the velocity of transmission of luminous rays, that the light of remote heavenly bodies presents us with the most ancient perceptible evidence of the existence of matter." The fundamental fact that when we look out into space, we also look back in time to the beginning, was not openly explored in the Victorian universe. Lord Kelvin, in 1901, coincidentally the year that Queen Victoria died, performed what no astronomer had dared. In the article, On Ether and Gravitational Matter Through Infinite Space, he made the relevant calculations on the connection between the age of the oldest luminous stars and the age and extent of the visible universe. However, evidence from the heavens of the cosmic age came too late. The cosmochronology of Genesis had already been controverted by geologists, who showed that the universe's age must be measured not in thousands, but in millions, and perhaps even billions of years. Geology. James Hutton, a Scottish farmer and physician, proposed in 1785 that the formation and erosion of mountains are continuous processes that have acted over an indefinite period. From the evidence, he found no vestige of a beginning, no prospect of an end. This marked the beginning of the steady-state uniformitarian principle, as powerfully argued by Charles Lyell. The landscape is continually modified by mountain uplift, erosion, and sedimentation, and the surface remains relatively unchanged. Into this picture of an Earth of great, if not unlimited age, fitted Charles Darwin's theory of evolution, presented in 1859 in his book On the Origin of Species by Natural Selection. On the one hand, catastrophists believe in a world periodically visited by catastrophes, while uniformitarians, on the other hand, believe in a steady-state world governed by natural laws. The controversy between the two schools persisted until the end of the 19th century, far more heated than the debate between the Big Bang and steady-state schools of the 20th century. In the second half of the 19th century, the uniformitarians were attacked by physicists under the leadership of Lord Kelvin. Calculations, now known to be inapplicable, on tidal effects and terrestrial heat losses suggested that the Earth could not be as old as geologists claimed. The calculated age of the Sun was the most decisive. Kelvin adopted Hermann von Helmholtz's idea that gravitational energy released by the slow contraction of the Sun fueled the Sun's luminosity. He estimated the Sun's age to be 20 million years. Because a luminous Sun is essential for life on Earth, this implies that fossils could not be older than 20 million years. The insistence by the physicists during this short period created dismay in the Earth and life sciences, and attempts were made to fit geological history and the evolution of life into Kelvin's short chronology. In the early 20th century, physicists redeemed themselves with radioactive dating methods and showed that the Earth's age is measured in billions, not millions of years. Ernest Rutherford, in his book Radiation and Emanation of Radium, 1904, wrote, "The discovery of the radioactive elements, which in their disintegration liberate enormous amounts of energy, thus increases the possible limit of the duration of life on this planet, and allows the time, claimed by the geologist and biologist, for evolution. The Victorian universe is falling. The Stoic and Epicurean systems have been competing with each other for a long time, with their popularity fluctuating over 2,000 years. This ended in the early 20th century. In the late Middle Ages, the medieval universe of celestial and angelic spheres evolved into a Stoic system of celestial spheres, immersed in an infinite and mysterious void. Then, the excellent poem De Rerum Natura, discovered in 1427, burst on the scene, opening the minds of Western Europeans to the dizzy prospect of a vast Epicurean system. Nicholas of Cusa, Thomas Digges, Giordano Bruno, William Gilbert, and numerous natural philosophers, Cartesian and Newtonian, spread the message. But in the 18th century, the evidence was confusing. The pendulum eventually swung again in the 19th century, and the standard model of the universe was a one-island Stoic system. In the early decades of the 20th century, the old debate once more flared up. Are we the inhabitants of a one-island or a many-island universe? Harlow Shapley, 1885 to 1972, an American astronomer studying the distribution of globular clusters, compact clusters of ancient stars, in 1918 overthrew the Herschel galactocentric system. He found that these clusters form a spherical distribution whose center lies tens of thousands of light years away in the direction of the constellation Sagittarius. A light year is the distance light travels in 1 year and equals 63,000 astronomical units. Shapley observed that the globular clusters belong to our galaxy, suggesting that the galaxy's center is also the center of their distribution. Jan Oort, a Dutch scientist, confirmed this result. Astronomers confirmed this result by showing that the stars of the Milky Way are orbiting around the distant center. In the early 1920s, Shapley supported the one-island universe, while Heber Curtis, another American astronomer, supported the many-island universe. Shapley thought the globular clusters were farther apart than they were, which made the galaxy appear much too large. Curtis, on the other hand, thought the stars were closer together than they were, which made the galaxy look much too small. Shapley defended the Victorian idea of a giant galaxy until 1930, when he finally gave up. This battle of ideas, known as the Great Debate by some historians, marked the culmination of the long-standing conflict between the Stoic and Epicurean systems. Ultimately, the Epicurean-like system, first proposed by the ancient world's atomists, prevailed. There was still a mystery. Our galaxy seemed much bigger than other galaxies. Walter Baade solved the mystery in 1952 by separating population on I and the SK stars, as well as the Cepheid variables of these two types of stars. This made the distances and sizes of other galaxies appear twice as large, and the Milky Way no longer seemed too small. Thoughts. 1. Immanuel Kant, a scientist and philosopher from Königsberg, published a deep-searching philosophy in 1781 called Critique of Pure Reason. According to Kant's philosophy, the world of sensations is organized into meaningful perceptions by an activity of a priori, subconscious, ideas of primitive origin. These primitive ideas from all past experiences of the species are essential for making sense of our fleeting and disjointed world of sensations. In Plato's philosophy, the ideas that organize our experiences belong to the universal mind. In Kant's philosophy, they belong to our minds. 2. William Herschel said that astronomy and botany have a lot in common. In a paper called On the Construction of the Heavens, he wrote, "This way of looking at the heavens seems to give them a new kind of light. They now resemble a lush garden, featuring a diverse array of products and options in various flourishing beds. One benefit we can at least get from it is that we can extend the range of our experience for a very long time." To continue with the vegetable analogy, isn't it the same thing whether we see a plant grow, bloom, grow leaves, produce seeds, fade, die and rot, or whether a lot of examples from every stage of the plant's life are shown to us all at once? We don't study one oak tree by itself for a long time to learn how it grows. Instead, we study many oaks in a forest at different stages of growth. The same goes for stars. Richard Proctor wrote in Our Place Among the Infinities, 1876, about how William Herschel's ideas about the universe changed. As the work went on, Sir William Herschel became less sure. He began to notice signs of a complex structure, which contradicted his method of measuring stars. He also realized more and more, as he continued his survey, that the depths of the stars were, in fact, unfathomable. The main goal of observational astronomy is to make catalogues that list positions, descriptions, and spectral compositions. Charles Messier, 1730 to 1817, a French astronomer and avid comet hunter, made a catalogue of 103 nebulae. He did this so that astronomers would not confuse these same nebulae with comets just beginning to shine. The Messier nebulae are prefixed with the letter M. Thus, M1 is the Crab Nebula, described as whitish light and spreading like a flame, and M31 is the Galaxy in Andromeda. William Herschel published catalogues that listed the positions and descriptions of thousands of nebulae. John Herschel continued this work and published the General Catalogue GC in 1864. This was the first systematic survey of the entire sky, containing 5,000 nebulae and star clusters. The GC was replaced in 1890 by the new General Catalogue, NGC, and subsequent supplements, index catalogues, were added. Thus, the galaxy M31 is also known as NG, C224. We are told that Napoleon Bonaparte, Emperor of the French, said to Laplace about his celestial mechanics, "You have written this huge book on the system of the world without once mentioning the author of the universe." Laplace replied, "Sire, I did not need that hypothesis." Whether true or not, this story shows the difference between theism and deism. Theism is the belief that God created and governs the universe. Deism, on the other hand, emerged during the Age of Reason and holds that God created a self-sustaining universe. Newton was a theist, Laplace a deist. 5. Hierarchical astronomy gained respect. John Herschel and Richard Proctor made it a real possibility when they suggested it as a way to solve the riddle of darkness at night. The Irish physicist Fournier d'Albe in England and the Swedish astronomer Carl Charlier in the early 20th century adopted this idea. Charlier, whose work garnered significant attention, demonstrated that stars do not cover the sky, and the night sky remains dark if the density of the clusters decreases rapidly with increasing size, corresponding to a fractal dimension of 2 or less. Fournier d'Albe proposed the hierarchical idea that the visible universe is only one of a series of universes containing solar systems of increasing size, arranged such that the solar systems in one universe are analogous to the atoms in the next higher universe, and so on. He demonstrated that in universes created this way, the night sky is dark. The gathering of stars into galaxies, galaxies into clusters, and clusters into superclusters constitutes what astronomers often call a hierarchy. Strictly speaking, this is a misuse of the word. A hierarchy is a pecking order organization that usually, but not always, consists of human beings, in which each member bosses those below and obeys those above. Government agencies and large businesses are hierarchies. The medieval universe, with its angelology and demonology, was also characterized by a hierarchical structure. The technically correct word for Kant's hierarchy is multi-level. A complete multi-level universe, an infinite number of levels in an infinite universe, according to Kant and Lambert, has an ultimate cosmic center at the highest level. This center, however, is at an infinite distance, and its reality is open to debate. Fournier-Dalbe and Charlier showed that the total amount of matter in a multi-level universe is much less than in a uniform universe. The mass and volume of the clusters steadily increase at higher and higher levels, and for clusters to stay separated from one another, their volume must grow faster than their mass. The average density, mass divided by volume, steadily decreases as the scale increases. In an infinite multi-level universe, the density of matter averaged over an infinitely large scale is vanishingly small. A finite hierarchy, with a finite number of levels made up of stars, star clusters, galaxies, galaxy clusters, and superclusters, best represents the clumpiness of the observed universe. The universe may be uniform on scales larger than superclusters, but this is not certain. 6. We learn about the heavens by studying what comes to Earth. In ancient astronomy, people used optical instruments with color descriptions to make observations. In the new astronomy, people used optical instruments with spectral decomposition to make observations. In modern astrophysics, scientists utilize a wide range of electromagnetic radiation: radio, microwave, infrared, optical, ultraviolet, X-ray, and gamma ray, as well as particle radiation, cosmic rays and neutrinos, and meteorites. Before the advent of new astronomy, everyone believed that the chemical composition of stars was forever unknown. Auguste Comte, a French mathematician, philosopher, and humanist, expressed this belief in his Cours de philosophie positive, 1830 to 1842. Any research that cannot be reduced to actual visual observation is excluded where the stars are concerned. Hey, we can see that it is possible to find out their shapes, distances, sizes, and movements. Still, it's hard to believe that we will ever be able to study their chemical makeup or mineral structure in any way. 7. The observatory became a meeting place where terrestrial chemistry was brought into direct touch with celestial chemistry. William and Margaret Huggins, Atlas of Representative Stellar Spectra. An article in the magazine Good Words, without a byline, instructed readers on how to create their spectroscope. This sparked Margaret Lindsay's interest in the emerging science of spectroscopy. She loved taking pictures and was also an astute observer of the sky, using the tools she made. William Huggins, the author of the article, happened to be in Dublin to check out his new telescope, which Howard Grubb had made. Spectroscopy brought them together, and they got married in 1875. They worked together, with him having bad eyesight and her having good eyesight, to make observations that helped start the new field of astrophysics. They utilized the latest photography and spectroscopy techniques to accomplish this. Queen Victoria knighted William in 1897 and gave him the Order of the Bath for the great contributions which, with his gifted wife, he has made to the new science of astrophysics. Harrison, Darkness at Night. 8. For a long time, the cosmic consequences of a finite speed of light received little attention. Occasionally, astronomers pointed out that light travels a finite distance in a finite period. One or two expressed wonder that we see astronomical bodies as they were thousands and millions of years ago. The implication that the universe is at least as old as the time it takes for light to travel from its farthest visible regions was either overlooked or set aside in articles, books, and lectures, possibly because it contradicted prevailing religious dogma. The embarrassing thought that when we look out into space to the limit of the visible universe, we see things as they were in the beginning, when the universe was created, rarely surfaced in pre-relativity Victorian days. Many astronomers in Britain were ordained members of the Church of England, and astronomy, being the most socially respectable and religiously acceptable of the sciences, was in the business of revealing God's works, rather than contradicting scriptural records. God appeared to be only the clockmaker, the being who had shaped the atomic parts, established the laws of their motion, set them to work, and then left them to run themselves. Thomas Kuhn, The Copernican Revolution, 1957. Are you a theist or a deist? Do you want a universe created and controlled by a divine power, or a universe that runs itself? 4. Make a two-dimensional fractal with 3 levels and find the fractal dimension d. What does it mean when d is less than 2? Build a fractal yourself. Use simple items like toothpicks and small rubber balls to create a 3-dimensional, 3-level fractal, and then determine its fractal dimension. 100 galaxies, each the size of 1, make up a cluster the size of 10. 100 clusters make up a supercluster the size of 100, and so on. What is the fractal dimension? Kant envisioned a multi-level universe that spanned an infinite amount of space and had an endless number of levels. He said that this universe has an ultimate center. But this is strange. Is it possible to have a center when the density is 0 on the largest scale? The universe is everything, even the thoughts we have about naming it. But what is the universe itself? Do we not know anything? It has various meanings for different people. For religious people, it's the theistically created world ruled by supernatural forces. For artists, it's a beautiful world revealed by sensitive perceptions. For professional philosophers, it's a logical world made up of analytic and synthetic structures. For scientists, it's a world of controlled observations made clearer by natural forces. It can also be all of these things at different times. People from many cultures, such as the Australian Aboriginals, Chinese Inuit, also known as Eskimos, Hindus, Hopi, Maori, Navajo, Polynesians, and Zulus, have very different ideas about the cosmos. Cosmic images change as people learn more and cultures mix. So in Europe, the medieval picture changed into the Cartesian, Newtonian, Victorian, and finally the Einsteinian picture as a result of the rise of Islam. The Victorian standard Western global vision from the late 1800s was very different from the Einsteinian one 100 years later. Every time and place makes a different cosmic vision, like a mask that fits the face of the future universe. When we discuss the universe, it is essential to clarify the various models of the universe. Each one, religious, artistic, philosophical, or scientific, is just one of many ways to view the universe, much like the various models employed by different cultures. In the past, scientists have categorized us into groups, such as the Pythagoreans, atomists, Aristotelians, and others. We should discuss the Pythagorean model of the universe, the atomist model of the universe, the Aristotelian model of the universe, and others. Ultimately, the models are given shorter names, such as the Pythagorean universe, the atomist cosmos, and the Aristotelian universe. We also get confused when we use the word universe to mean a model of the cosmos. The term universe has another significant issue. When we use it by itself, without specifying the model we have in mind, it suggests that we know what the universe is really like. We discuss the universe as if it has finally been discovered and revealed, just like many people have done in the past. By calling the current model of the universe, we overlook the fact that it will likely end up like the models that came before it. We often mistake the mask for the face, the model universe for the real universe. Our ancestors made this mistake frequently, and our descendants will likely look back and see us repeating the same error. The Pythagorean universe, the atomist universe, the Aristotelian universe, and so on. Each universe is a mask, a cosmic picture, a model that is invented, modified as knowledge advances, and finally discarded. We may avoid directly referring to the true nature of the universe, which we cannot guess, even in our wildest imaginings. When people say the vastness of the universe, they refer to the extent of the universe as modern science has revealed it to us so far. They use the word freely and loosely, without always remembering that the universe is still mysterious and unknown. You should always ask yourself, what does life mean? What is the universe's secret? What started it all? What will happen in the end? Do these questions make sense? We all say the words of Erwin Schrödinger. I know not whence I came, nor whither I go, nor who I am. We all look for the answer. The search is doomed to fail from the start until we learn about past worlds, and especially the present cosmos. Cosmology is a collaborative effort of science, philosophy, theology, and the arts that seeks to determine what is fundamental and unifying in the universe. It draws on information from other fields, such as physics and astronomy, to assemble a comprehensive cosmic picture that encompasses everything, which is the primary focus of this podcast. We explore the small-scale and large-scale domains of the universe. We delve deeply into the microscopic worlds of cells, molecules, atoms, and subatomic particles, while also exploring the vast macroscopic realms of planets, stars, galaxies, and the universe. We find that the minimal and the large are intimately related in cosmology. Daily, we deal with ordinary things like plants and flower pots. To understand these things of sensible size, we explore the small-scale and large-scale domains of the universe. Since the 17th century, knowledge has advanced rapidly, and the number of scientists has grown enormously. Each science focuses on a domain of the universe and tends, over time, to fragment into closely related new sciences of greater specialization. Originally, the characteristics of living and non-living things defined the differences between the broad domains of biology and physics. As it advanced, this basic science branched into new ones, which in turn became more specialized. Physics, once known as natural philosophy, has evolved and branched into various subfields, including high-energy subatomic particle physics, low-energy nuclear physics, atomic physics, chemical physics, condensed matter physics, biophysics, geophysics, astrophysics, and others, each with its theoreticians, experimenters, and technicians. Biology, once the subject of naturalists with broad interests, has evolved and branched into associated sciences, including botany, zoology, entomology, ecology, paleontology, and others. And astronomy, once the subject in which everybody had equal knowledge, but not computing skill, has branched into planetary sciences, the study of stellar structure and atmospheres, interstellar media, galactic astronomy, extragalactic astronomy, and the separate fields of radio, infrared, optical, ultraviolet, X-ray, and gamma-ray astronomy. A person who studies a branch of science in depth becomes a specialist, surrounded by a web of detailed knowledge. They possess extensive knowledge about a small part of the universe, yet remain relatively uninformed about the rest. The sciences break the universe down into smaller and smaller pieces, focusing increasingly on detail. Cosmologists take a broad view. Unlike other scientists, they keep their distance from their canvases to avoid getting too distracted by small details, just like Impressionist painters do. Cosmology is the only science where specialization is a bit tricky. Its primary goal is to put together the cosmic jigsaw puzzle, not to study any one piece in detail. Introductory cosmology is not a branch of astronomy. It is a cosmopedia, more than an inventory of the universe's content. The universe is not a whole universe catalogue of descriptive astronomical data. Cosmology is the study of the primary cosmic constituents, including the origin and history of the chemical elements, as well as space and time, which form the framework of the expanding universe. Large space regions scatter the primary things of importance and endure for long periods. The origin and evolution of stars and galaxies, as well as the origins of life and intelligence, are essential cosmic subjects. Subatomic particles, their role during the earliest moments of the universe, and subsequent combinations into atoms and molecules that form the complexity of the living cell and our surrounding world, are all of cosmic interest. At every turn, cosmology prompts us to pause and reflect. There are still many important things that are not fully understood, such as how we learn to speak, how our brains grow, and how we can create abstract mental structures and think in numbers. The way people think also influences the design they perceive in their universe. People are an essential part of cosmology because they represent the universe as it perceives and experiences itself. Who are the cosmologists? Professional cosmologists are relatively few. They are well versed in mathematics, physics, and astronomy, and study the evolution and large-scale structure of the physical universe. In general, however, people become cosmologists whenever they seek to understand the universe. When we stand back from the study of a specialized area of knowledge, or step aside from our everyday affairs, and reflect on things in general, and try to see the forest, and not just the trees, the whole painting and not just the dabs of paint, and the entire tapestry, and not just the threads, we become cosmologists. Cosmology has been around as long as humans have. It started when early humans, who lived in small groups, learnt to talk and tried to make sense of the world around them. Hundreds of thousands of years ago, people probably explained their world in different ways. They thought that spirits of all kinds, driven by human-like impulses and passions, controlled everything. Early people projected their inner thoughts and feelings into an outer, animistic world, where everything was alive. By making offerings, prayers, and gifts to the spirits, humans were able to control the events of their world. It was the age of magic, a time when benign and demonic spirits were incarnate in plant, animal, and human form. Ambient and indwelling spirits' passions, motives, and actions explained everything that happened readily and easily. It was an anthropomorphic world of the living earth, water, wind, and fire, into which men and women projected their emotions and motives as the guiding forces, the kind of world children read about in fairy tales. From this golden age comes our primeval fear of the menace of darkness, the rage of storms, and our enchantment with the wizardry of sunrises, sunsets, and rainbows. For reasons not yet fully understood, human beings everywhere remained one species, and cultures, languages, social codes, belief systems, laws, and technologies were interchanged. Possibly, our modern moral codes, which regulate behavior in families and society and generally determine what is considered ethically right and wrong, were naturally selected over extended periods in primitive societies. Societies deficient in codes of mutual care and support among individuals had little chance of surviving. At the dawn of history, approximately 10,000 years ago or earlier, the early city-states emerged. More abstract concepts of the universe's magic evolved into the myth universe, and the long age of magic led to what might be called the age of theism. The spirits that had been everywhere, activating everything, amalgamated, retreated into remote mythic realms, and became powerful gods who personified abstractions of thought and language. In The Golden Bough, James Fraser speculated on how magic among primitive people evolved into theism, and how the magic universe transformed into various mythic universes. With the growth of knowledge, man learns to realize more clearly the vastness of nature and his littleness and feebleness in the presence of it. However, recognizing his helplessness does not carry with it a corresponding belief in the impotence of those supernatural beings with which his imagination peoples the universe. On the contrary, it enhances his conception of their power. If he feels so frail and slight, how vast and powerful must he deem the beings who control the gigantic machinery of nature? For those who thought more deeply, religion gradually replaced magic, which had posited that powerful spiritual beings controlled natural events based on their desires or whims, much like a kind person but with greater power. Many myths include simple images of the cosmos: the Sumerian, Assyrian, Babylonian, Minoan, Greek, Chinese, Norse, Celtic, and Mayan mythologies, among others, are of historical interest because they show how people used to think about the universe. Creation myths, which are often complicated and hard to understand, are especially fascinating. Men and women everywhere were at the center of an anthropocentric universe. The university was primarily composed of people, and the legendary gods continued to serve and protect humans, regardless of their strength or distance from them. Anthropocentrism formed the basis of Greek cosmology, which centered on an Earth-centered universe. The universe of Aristotle in the 4th century BC was geocentric, or Earth-centered. The spherical Earth rested at the center of the universe, and the moon, sun, planets, and stars, fixed to translucent celestial spheres, revolved around it. The innermost region of heaven, the sublunar sphere between the Earth and the moon, contained earthly and tangible things in an ever-changing state. And the outer areas of heaven, the celestial spheres, contained ethereal and intangible things in a never-changing state. This system's subsequent elaborations, which brought it closer to agreement with astronomical observations, culminated in the Ptolemaic system around AD 140. The Middle Ages, 5th to 15th centuries, were not as dark as was once thought. From the 13th to the 16th century, the medieval universe was perhaps the most satisfying form of cosmology known in history. Christians, Jews, and Muslims were blessed with a finite universe in which they had utmost importance. By the standards of the Arab and European worlds of that time, it was a rational and well-organized universe that everyone could understand. It gave location and prominence to humanity's place in the scheme of things, provided a secure foundation for religion, and gave meaning and purpose to human life on Earth. Never before or since has cosmology served the everyday needs of ordinary people in such a vivid manner. It was simultaneously their religion, philosophy, and science. The Copernican revolution changed the finite geocentric universe into the infinite, centerless universe. In the 16th century, Nicholas Copernicus crystallized trends in astronomical thought that had originated in Greek science almost 2,000 years earlier, and proposed the heliocentric or sun-centered universe. The Copernican heliocentric universe soon evolved into the infinite and centerless Cartesian universe, which, in turn, was followed by the Newtonian universe revolution in outlook that dominated the 16th and 17th centuries. The Copernican revolution opened the way for modern cosmology. However, the spiritual university is far more critical than the physical university, which is overly anthropocentric. The universe is the great chain of being, a chain of countless links that goes from human beings through all the lower forms of life to inanimate matter and up to the throne of God. Humanity was the central link between the angelic and brute worlds, even in an infinitely large physical universe, which lost the Earth and then the Sun as its natural center. It was still possible to hold on to old ideas that made human beings seem central to the cosmic drama. The gods were always mysterious, and after the Copernican revolution, they became even more mysterious. In the middle of the 19th century came the most dreadful of all revolutions, the Darwinian Revolution. Humans, previously the central figures in the cosmic drama, began to resemble the creatures of the field. The gods, who had attended and protected humanity for so long, were cast out of the physical universe. The anthropomorphic, magic, and anthropocentric, mythic universes were wrong in almost every detail. The medieval universe and the concept of the great chain of being have been discarded. Finally, science triumphs, dispelling the myths and superstitions of the past. We applaud the Renaissance, 15th to 16th centuries, with its revival of art and learning. We applaud the rise of the Cartesian and Newtonian world systems in the 17th century, 17th century. We applaud the Age of Reason, the Enlightenment of the 18th century, with its conviction in the power of human reason. We applaud the Age of Science, 17th to 20th centuries. And we too easily forget the growing dismay of ordinary men and women in a universe that, century by century, progressively became more meaningless and senseless. With the decline and death of the old universes, anthropomorphic and anthropocentric, humanity was cast aimlessly adrift in an alien universe. We also don't think the universe is like us, made in our image, or ruled by gods. It's not a magical place with spirits that look like people, and we're not the main characters. As Protagoras said, we measure the universe, which means that the cosmos is anthropocentric. Let's try to understand this idea. We have minds, or as some would say, we have brains. For our purpose, it is unnecessary to inquire into the nature of the mind-brain and attempt to probe its mysteries. Whether we consider the mind a non-physical entity of psychic activity or a physical brain engaged in bioelectrochemical processes, it remains irrelevant to our purpose. We have minds into which information pours via the sensory pathways, and from this information, we devise in our minds the Aristotelian, Stoic, Epicurean, Zoroastrian, Neoplatonic, medieval, Cartesian, Newtonian, and all the other universes that have dominated human thought in different ages. We observe plants, flower pots, and other things, and devise grand theories that relate and explain them. These theories reside not in the things themselves, but in our minds and brains. Different universes prevail at each step in the history of cosmology, and every university society is a grand mental edifice that makes sense of the human experience. Each anthropomorphic universe consists of ideas devised by human beings as they seek to understand what they observe and experience. For those who feel lost in the vast and meaningless multiverse, it's comforting to know that all universes are anthropomorphic. Men and women made and measured the medieval universe, a concept that medievalists would have strongly denied. The modern university, which resets its bioelectric chemical brains to think about it, is also human-made. Like the medieval universe, other universes will inevitably take their place as time goes on. The future universes will almost certainly be different from our modern version, but they will all be anthropocentric because, as Socrates said, man is the measure of all things. Of course, the universe is not human-made, but we have no true conception. All we know is that it contains us, the dreamers of universes. Cosmology and society. Every institution has a history that affects how its society works. Cosmology and culture are very closely linked. There is a universe where a society exists, And within that society, there is a society of thought, which in turn exists within a universe. In primitive cosmology, mythology and society are closely intertwined, and the ways of gods and goddesses are similar to those of men and women. For example, cruel people often create cruel gods who condone cruel behavior, while peaceful people create gods that promote calm behavior. The relationship between cosmology and society is as strong as ever, if not stronger, but it is often less obvious. The principle of plenitude, which dates back to Plato, has had a profound impact since the 15th century. The ideas that come from universities are, without a doubt, the most potent and influential in any society. These ideas shape histories, inspire cultures, spark wars, build kingdoms, establish empires, and establish political systems. The principle of plenitude comes from the anthropocentric idea that an intelligible supreme being made the universe for humans. In its simplest form, it suggests that a benevolent creator has endowed humans with a planet full of resources to utilize. The formal argument is as follows. The supreme being is without limits because limits imply imperfection, which is against belief. The unlimited potential of the supreme being is shown in the created world's unlimited actuality. The earth must show every form of reality in endless abundance. This is the principle of plenitude that fills Western culture. The principle of plenitude was proven by the fact that there was an endless supply of everything. Europeans originated the idea, followed it, and then disseminated it to the rest of the world. Telescopes revealed the richness of the heavens. Microscopes showed the world to be teeming with life. And sailors' voyages around the world opened up incredible views of a vast and bountiful earth. The principle of plenitude shaped political ideologies. It promised endless untapped wealth and allowed free enterprise to grow like never before. To stop depletion and population growth, people had to push further east and west towards the alluring rewards of untouched lands. Adam Smith once said, "The true cost of anything is the effort and difficulty involved in obtaining it. Go east. The streets are paved with gold. Go west. Beyond the sunset lie lands of unharvested wealth." The philosophy of plenitude did not include the idea of husbandry of finite resources. People were sure that everything existed in unlimited abundance. When anything became exhausted, like the bison herds, the carrier pigeons, and the great auks, they were taken by surprise and felt cheated. Karl Marx wrote, "In the Communist Manifesto, we are told that the less wealthy have nothing to lose but their chains. They have a world to win." Sadly, the idea of plenitude, which is now deeply embedded in our cultural heritage and has been spread in many ways around the world, is nothing more than a cosmological myth. We are living in a time of crisis. The population is growing too rapidly, resources are depleting, and the environment and atmosphere are becoming increasingly polluted. We are also fascinated by prophecies of doom. Many of the old ideas we have about the universe are still ingrained in our minds, but they no longer apply in the modern world. We are stuck in the flawed logic of outdated academic theories that could harm us. This event, more than any other, marked the beginning of the Industrial Revolution, which has profoundly changed the way we live and work. Some people argue that the problems we face today are a result of the Industrial Revolution. But it's not the technologies themselves that are to blame. Instead, it's the ideas and beliefs that guide how we utilize them. To make things more straightforward, let's say that space travelers come across a planet that has been destroyed by uncontrolled technology and is now lifeless. The space travelers can't just assume that technology caused the destruction when they look into it. They need to look for evidence that reveals the beliefs of the people who lived there. How did the beliefs of the people who lived there affect their broken world? They will probably say in their reports that The ruined world is the result of ancient cosmology. This is a cosmology based on ideas that the people who lived there had rejected at times when they were more rational, but that had led them to their doom. In cosmology, there are two different languages, one for universes and one for cosmologies. In the first, cosmology is the study of many universes, each with its model. Cosmological research typically examines the universe as we know it today. Second, different societies have their cosmologies, which study the universe. We either have one cosmology that examines many universes, or many cosmologies that examine one universe. The first one discusses universes extensively, and the second one focuses on the universe. We use the first method in this podcast because it doesn't use the word universe very often, and when it does, it's only to make a point more straightforward. This way, it doesn't give the impression that the universe is a known or even knowable thing. For approximately 1 million years, Homo sapiens has existed. What did early humans think about the world around them? Bronislaw Malinowski wrote in his book about the Trobriand islanders of Melanesia. I will ask my readers to step out of the theorist's closed study and into the open air of the logical field. We learn from his observations and those of many other anthropologists who study different societies that there are primitive and advanced cultures, as well as complex languages, all over the world. There are probably no truly primitive people left in the world today. They would give us a glimpse into how our distant ancestors thought and lived. Edward Tyler, a Victorian anthropologist, wrote in his book Primitive Culture that the world of primitive people was filled with spiritual beings. He developed the concept of animism. People in the past projected their feelings and reasons for doing things onto the world around them. This made the world come alive and could explain almost anything that needed explanation. As language and abstract thought evolved, the spirits around us transformed into powerful nature. Spirits, gods, and goddesses. James Frazer wrote in The Golden Bough that the concept of gods as superhuman beings with powers far beyond those of humans has evolved slowly throughout history. He observed how animism evolved into theism and how the gods came to dominate the gigantic machinery of nature. In general, it's hard to define religion. It includes thoughts and feelings. People in all cultures share the same religious sentiments, but the religious ideas that evoke these feelings vary across cultures. Religious feelings are a natural part of being human and are necessary for societies to survive. The study of religious ideas is called theology, and faith is the belief that those ideas are true. The ideas always have cosmological meaning. People in different societies have shared similar religious sentiments throughout history, but they have held very different religious beliefs, each of which their followers believed was correct. The fact that religious feelings are the same for everyone and that there are many other religious ideas shows that Frazer was wrong when he said that religion started with the birth of gods. Religion may have existed as long as humans have inhabited the earth. A lot of people make the mistake of mixing up religious feelings with religious ideas. When people in religious groups insist on keeping their mythic beliefs, they don't realize that they are mixing up theory with emotional experience, and that they can't have religion without primitive cosmology. They don't understand that when science rejects mythic cosmology, it doesn't mean that science and religious experience are at odds with each other. For example, the modern theory that light is composed of tiny particles of energy has not diminished our ability to perceive color or the emotions associated with it. Mythology is the study of stories and ideas that help us understand how other civilizations, often older ones, thought and believed. Myths are believable in the cultures where they first appeared, but they become unbelievable when they are moved to other cultures' belief systems. Cosmological ideas have a significant influence on the concepts of virtue and evil. Thou shalt not suffer a witch to live. It is thought that in the witch universe of the late Middle Ages, the Renaissance, and the Age of Reason, the Enlightenment, about 500,000 men, women, and children confessed to witchcraft and heresy under torture and were burned to death. People said that heretics would burn forever in hell, but the temporary pain of fire on earth was worth it if it meant they wouldn't have to go to hell. Here is an example of the saying, "Cruel people make cruel gods who allow cruel behavior." And the terrible thing was that every time one witch was found and the right tools were used to look into it, many more witches appeared. Their numbers grew and seemed to be endless. Fire consumed the male and female witches and their evil, and they continued to multiply. These horrible creatures seem to have power over all of Christianity. We are finding more and more of them in countries we didn't know existed before. All modern observers agree that they have gained previously unknown powers, a complex international organization, and social habits that are highly advanced. Some of the most intelligent people of the time stopped studying the human sciences to learn more about this new continent, which they referred to as America of the spiritual world. The details they found are constantly and amply confirmed by other research workers, experimenters in confessional and torture chambers, theorists in libraries and cloisters, leaving the facts more securely established and the prospect even more alarming. Rather than facing extinction, the witches surged in number, seemingly poised to overwhelm Christendom with the powerful forces of triumphant evil. Protesting against witch hunting as inhumane during a time of emergency was sheer lunacy, condemned by the popes as bewitchment and the result of consorting with devils. Scientists view their theories and concepts differently, whereas philosophers and theologians have an emotional commitment to them that compels them to believe in them. Scientists are concerned with creating many theoretically coherent options, leaving any assessment of their truth to observation. Suggesting several mutually exclusive hypotheses for the same occurrence does not make scientists uncomfortable. Scientists look at their theories and ideas in a different way than philosophers and theologians do. Philosophers and theologians often feel emotionally invested in their ideas, which makes them more likely to believe in them. Scientists are more interested in generating a multitude of theoretically consistent options and leaving it to observation to determine which ones are true. Scientists don't mind suggesting multiple hypotheses that can't all be true at the same time. Herbert Butterfield says in The Origins of Modern Science that it outshines everything since the rise of Christianity and reduces the Renaissance and Reformation to the rank of mere episodes, and looms so large as the real origin both of the modern world and the modern mentality that our customary periodizing of European history has become an anachronism and an encumbrance. Butterfield argues that science saved Europe from the chaotic world of superstition and witchcraft. The arts, religion, or sciences do not quell the Renaissance's witch frenzy. Science was contacting a new cosmos, more suited for defining the boundaries of human influence over nature and separating the supernatural from the natural. Maybe the world of external facts is much more fertile and plastic than we have thought. It could be that all these cosmologies and many more analyses and classifications are real ways of organizing what nature gives us to understand, and that the main factor that decides which one we choose is something inside us rather than something outside of us. Natural science describes nature as being open to our questions. It is a part of the interaction between nature and ourselves. It does more than just describe and explain nature. C.S. Lewis writes in The Discarded Image, "The old masters do not take any model nearly so seriously as the rest of us." Later he says, an unprovoked assault of new facts, as unprovoked as the nova of 1572, may violently destroy our model. Still, I believe it is more likely to change when far-reaching changes in the mental temper of our descendants demand it. We won't create the new model without proof. It will emerge when the inner desire for it becomes sufficiently strong. It will be factual evidence. Still, nature offers most of her proof in response to our inquiries. Long before Darwin, the idea of missing links came from the great chain of being. In Arthur Lovejoy's The Great Chain of Being, we read, next to the word nature, the sacred phrase of the 18th century, playing a somewhat analogous role to that of the blessed word evolution. Lovejoy claimed that the concept of the great chain of being was closely related to the idea of plenitude. Not so long ago, people thought the planet was virtually inexhaustible in its capacity to meet human needs. In The Tragedy of the Commons, Garrett Hardin looks at how myths and cosmological ideas from the past affect our lives today. People often believe that ownership is a natural and divine right, so they strive to acquire as much of a shared resource as possible. Every herder wants to grow his herd, so he grazes his animals on land that is shared with others. Disease and tribal warfare help keep the balance by keeping the number of people and animals below the land's capacity. Then, when life becomes more complex, sadly, most problems caused by old cosmic myths, such as the great chain of being, the principle of plenitude, and the ability to reproduce without limit, don't have technological solutions. Everyone is racing towards the end of the world. I believe that the population problem, as it is usually understood, is a type of human problem known as a technical solution problem. A technical solution may be defined as one that requires a change only in the techniques of the natural sciences and demands little or nothing in the way of change in human values or ideas of morality. Most people who worry about the population issue are fair to say. Farming the oceans or making new kinds of wheat will fix the problem in a technical sense. Astrology was the study of planets and stars in the ancient world and the Middle Ages. Astrolatry was the worship of stars, and astromancy was the practice of soothsaying and divination that used the positions of stars. We should use astrology to study stars, but we call the study of living things biology. Astrology, on the other hand, evolved and replaced astrolatry and astromancy, which had become corrupted. Astrology is based on the myth that the movements of celestial bodies influence human behavior. Millions of Americans read astrological, or astromancy, articles in their daily newspapers. They find astromancy interesting and fun because it is centered on people and connects them to the universe in ways that most people find relevant and meaningful. Some people take it seriously, but by today's standards, it seems silly. However, most people find it interesting because it taps into aspects of our cultural heritage that remain intact. In Objections to Astrology, Bart Bok, Lawrence Jerome, and 19 other well-known scientists express their dismay at how widely accepted astrology is becoming in many areas of life. People who still believe in astrology do so even though there isn't much scientific evidence against it. Talk about why astrology is still popular. Could many people end up in a meaningless world where their beliefs and religions are no longer relevant? How can we deal with this dire situation where people find comfort in astrology, which science is trying to get rid of? When I was a kid, Sunday schools didn't stop people from leaving religion. Would adding more introductory science classes stop people from leaving the scientific universe? In Science and the Modern World, Alfred Whitehead says, "Nature is a dull affair, boundless, scentless, colorless, merely the hurrying of material endlessly, meaninglessly. Thinking about Adam Smith's famous quote, "The real price of anything is the toil and trouble of acquiring it," is essential. We should consider the long-term impact of our actions on the environment. These results could mean that the people who inherit the later depletion and dispersion pay the real cost. Have we already seen the exact price? Put problems here that don't have a technical answer. Keep in mind that technical answers can sometimes lead to new problems. New medicines can help address old problems, but they can also exacerbate population growth issues and cause additional pain. Hardin believes that the rise in population necessitates a shift in human values or moral principles, as it is a problem that can't be solved solely with technology. Would taking up space help with population problems? Sebastian von Hoerner demonstrates in Population Explosion and Interstellar Expansion that this kind of effort could potentially solve the issue within at least 500 years, given the rise in birth rates. The human space bubble would expand indefinitely, and in 500 years, it would be traveling at the speed of light. Every planet that was colonized would become increasingly crowded and face the same problems we have on Earth. How much is the West to blame for the fantastic rise in human life and the decline in wildlife, with its ideas about abundance, drugs, cleanliness, and technology? The whole temple of man's achievement must inevitably be buried beneath the debris of a universe in ruins. All the labors of the ages, all the devotion, all the inspiration, all the noonday brightness of human genius are destined to be buried beneath. All the things, if not quite beyond dispute, are now so nearly certain that no philosophy that rejects them can hope to stand. The only safe place for the soul to live is on the scaffolding of these realities, which is built on a foundation of unending despair. Look at any issue closely enough, and the same excitement, wonder, and mystery come back. More information makes you want to dig deeper and find even more amazing secrets. We turn over each new stone with joy and confidence, revealing the weirdness we never imagined, which leads to more beautiful questions and mysteries. It's an incredible adventure, and we're never worried that the answer might be disappointing. 4,000 years ago, Babylonian sky-gazers divided the sky into the constellations of the zodiac, compiled star catalogues, and recorded the movements of planets. They invented multiplication tables, established rules of arithmetic, and were skilled in the arts of computation. By studying the rhythmic variations of the heavens, they predicted eclipses and prepared calendars that forecasted the seasons and dates of the full and new moons. All this was done as religious worship, astrolatry, and religious divination, astromancy. The Babylonian wizards charted the heavens, guided by mythic principles, and failed to develop natural explanations of celestial movements. The Greek philosopher-scientists attempted to explain the world's complexity by breaking it down into its fundamental components. The proposed parts, or primary constituents, were water, Thales, 6th century BC, air, Anaximenes, 6th century BC, seeds, Anaxagoras, 5th century BC, and atoms, Leucippus, 5th century BC. Fire, Heraclitus, 5th century BC. Earth, Xenophanes, 5th century BC. Empedocles described the elements of earth, water, air, and ether in the 5th century BC. In the 4th century BC, Aristotle described the four classical elements: earth, water, air, and fire, or ether. Thales said, "There is an ultimate substance from which all things come to be. It is being conserved." Scientists in the past sought to understand how things worked, so they drew on examples from crafts and the arts such as pottery and metalwork. They thought it was essential to keep things that could combine and recombine to form objects with different shapes and colors. They didn't believe in supernatural, mythological explanations for natural events. Instead, they broke everything down into its most basic parts and used the laws of conservation of energy. They made guesses and did experiments based on those guesses. This is what the scientific method is all about. The 6th century BC saw the rise of new and powerful ideas in the works of Pythagoras, Heraclitus, and Parmenides. Pythagoras of Samos, who started a school of advanced thought that had a significant impact, may have been the first to use the word philosopher. He taught that the earth is a sphere and that mathematical relationships govern the cosmos. Heraclitus of Ephesus, who was known as the weeping philosopher because he was so negative, said, "Everything changes, nothing lasts, and fire is the most important thing." He envisioned a universe of chaotic change, governed by a battle between opposing forces. He said that wisdom is knowing how things change. Parmenides of Elea said that nothing changes, everything lasts, and that wisdom is learning how to ignore sensory illusions. He envisioned a world of truth, beauty, and justice, where all change was merely an illusion of the senses. Heraclitus's ideas about constant change and Parmenides's ideas about an unchanging reality are very different. Heraclitus's ideas predict the Newtonian universe with its moving parts, while Parmenides's ideas predict the Riemannian spacetime, found in relativity theory. Harmony in Pythagorean terms. The Babylonian astronomers were priests and prophets, but the Hellenic, Greek astronomers were philosophers and scientists. The Babylonians excelled in math and abstraction, while the Greeks excelled in geometry and metaphor. Pythagoras imagined a universe of geometric harmony, with spheres, circles, and vortical motions as the basic shapes in the universe's design. Diogenes Laertius, 3rd century AD, stated that Pythagoras was the first to refer to the heavens, cosmos, and earth as spheres. The Pythagoreans thought that the heavenly bodies were spheres moving in perfect circles around a central cosmic fire that was too far away for mortals to see. The heavenly bodies made beautiful sounds, and their celestial symphony, or harmony of the spheres, was too far away for mortals to hear. Socrates. Socrates lived in Athens from about 470 to 399 BC. He taught the liberal arts and stressed the importance of humanistic studies. He changed the course of philosophy through his disciple Plato. Almost nothing he wrote has survived, and we know about his teachings through Plato's writings. Socrates believed that the immortal soul, or mind, inhabited a mortal house of clay. He stressed the importance of questions that begin with why, while Greek scientists, using examples from the mechanical arts, noted and emphasized the importance of understanding how things worked. If atoms truly explain the construction of matter, what does that mean? It is more important to understand why atoms exist, and only pure reason, searching within the soul, can determine their necessity and purpose. At the age of 70, he was sentenced to death for misleading his students with heretical thoughts. Plato. Plato, about 427 to 347 BC, established the first school of advanced learning in Athens, known as the Academy. Over the centuries, his teachings have had a profound influence on more people than those of any other philosopher. He interwove the Pythagorean and Socratic themes into a cosmology that stressed the wide difference between appearance and reality, between fugitive matter and concrete mind. The transitory, phenomenal world is only a shadowy image of the eternal real world. The mind governs the innately disordered, incoherent, and discordant matter, the source of order, coherence, and harmony. In the parable of the cave, Plato imagines people chained in a cave and unable to move. The light shines from behind them, illuminating the wall in front, but they cannot see it. Behind them, moving objects cast shadows on the illuminated wall. They remain chained throughout their lives, experiencing only the shadows on the wall. Surely, wrote Plato, such persons would believe the shadows to be the only realities. According to this parable, we are prisoners of our senses, and the intelligent mind can only reach the real world beyond the senses. 3. Cosmic systems in the ancient world. Aristotelianism, Epicureanism, and Stoicism. From the 4th century BC to the 3rd century AD, 3 rational belief systems, Aristotelianism, Epicureanism, and Stoicism, were the most popular in the Mediterranean world. Ea universus is a mix of philosophical, scientific, and ethical ideas. All 3 universes have left a lasting mark on Western culture. The Aristotelian universe of celestial spheres originated in Athens and was later adopted by the Jewish, Christian, and Islamic worlds. It evolved into a medieval universe by incorporating theistic elements from Babylonian and Zoroastrian traditions, and it endured until the 16th century. The Epicurean universe of endless worlds originated in Athens in the late 4th century and remained popular among educated and middle-class individuals for centuries. It combined atomist ideas, focused on the life sciences, rejected the gods as explanations for events in the natural world, and accepted the idea that men and women are equal. Later, the Judaic, Christian, and Islamic worlds condemned it for its atheism and tried to stamp it out everywhere. The Stoic universe, which originated in Athens in the 3rd century, gained popularity throughout the Roman Empire. It consisted of 2 parts: a finite cosmos of stars and an infinite void that extended beyond the observable universe. The Stoics stressed the importance of science and moral duties. The universe, according to Aristotle. The universe with 2 spheres. During Plato's time at the Academy in Athens in the 4th century BC, the Pythagorean 2-sphere universe was popular. It had a central sphere, the Earth, and an outer sphere, the stars. The planets moved in ways that were not known between the 2 spheres. Plato asked all serious students, "What are the uniform and ordered movements of the planets?" The universe has many spheres. Eudoxus, who studied under Plato, suggested that the universe could be represented by a central spherical Earth, surrounded by concentric rotating spheres. The outermost sphere rotated every day and held the stars, just like in the Pythagorean 2-sphere model. The intermediate spheres held the planets and rotated at different speeds around axes that were tilted at various angles. Initially, these genome trial devices were intended to serve as simple analogies for the mechanical and optical components of a modern planetarium. However, Aristotle transformed the analogy into a practical application. Aristotle, 384 to 322 BC, born in Macedonia and a student of Plato's Academy, founded his school, known as the Lyceum. He did this because he enjoyed teaching while walking around with his students. His interests were broad, and he wrote 150 volumes of lecture notes. He was a careful observer, and his main area of interest was the life sciences. He talked about the vast chain of being and how different life forms evolved. When Alexander the Great, his student and then patron, died, Aristotle was afraid of being accused of impiety against the gods. He fled Athens so that Athens would not sin twice against philosophy. Aristotle employed the many-sphere model, attributing both physical and etheric reality to the spheres. The planets, Moon, Mercury, Venus, Sun, Mars, Jupiter, and Saturn, were attached to the translucent spheres that rotated around the Earth. The motions of the planets and stars required up to 56 supporting spheres. The terrestrial elements of Earth, water, air, and fire, compose the Earth and inner sublunar sphere, and a fifth element, called ether, later known as quintessence, formed the outer celestial spheres. The natural motion of the terrestrial elements was up and down, whereby they sought to find their proper places according to weight. And the natural motion of the etheric element was endless revolution around the Earth. In Aristotle's universe, all motion needed a constant application of force. When bodies came into direct contact with each other, they pushed and pulled, causing them to move. Aristotle said that the void, or vacuum, couldn't exist because isolated bodies would be still. This meant that atoms, the smallest particles of matter, couldn't exist because there would be interatomic voids. Furthermore, if atoms did exist, as the atomist philosopher said, then no force could have direct contact. According to Aristotle, the whole Aristotelian universe was a cosmic sphere of finite size, necessarily finite, because its outer edge revolved around the Earth. If the heavens are infinite and revolve in a circle, they will travel an infinite distance in a finite time. This, we know, is impossible. Straight lines could not go on forever because they would go beyond the universe. So all the lines that followed each other were missing parts and weren't perfect, but the circles were. It made sense that the earthly parts of the perishable form would move up and down in an imperfect way towards and away from the cosmic center. This is why the Earth did not rotate. It was also right that the etheric part of the celestial spheres should only move in perfect circles. So, it's easy to see why the heavens keep moving. When something reaches its natural destination, it comes to a stop. But for the body, which naturally moves in a circle, every destination is a new starting point. Aristotle's universe was spatially finite in a steady state. It had existed unchanged through eternity, and its perfect motions had neither a beginning nor an end. Eudoxus's rotating spheres didn't explain why planets appeared to move backward, retrograde motion, and forward, prograde motion, across the sky, nor why they were brighter during their backward motion. The idea of eccentric circles was a step towards solving this problem. The Earth stayed at the center of the universe, but each celestial circle had its center moved a certain amount from the Earth's center. Another important step taken in the 3rd century, B.C., was the introduction of epicycles. The epicycles were extracircular motions that explained why the planets appeared to move backward and forward across the sky, and were brighter during their backward motion. Ptolemy. Claudius Ptolemy, dates unknown, an astronomer and mathematician at the Museum of Alexandria in the 2nd century AD, did for astronomy what Euclid, also at the museum 4 centuries previously, had done for geometry. He brought together many of the ideas and observations made in previous centuries. In his principal work, Almagest, the Great System in Arabic, he used eccentrics, epicycles, and equants. The equant, or equalizing point, is an off-centered point where the epicycle moves at a uniform angular rate. By combining eccentrics, epicycles, and equants, along with careful calculations, it became possible to accurately mimic the movements of the planets in a universe where Earth is at the center. The result was a geometric marvel. It endured for 1400 years until the revolutionary works of Copernicus, Kepler, and Galileo overthrew it. Ptolemy's version of the Aristotelian universe didn't include many advances in Greek science. For example, it didn't accept the idea of atoms, the Democritean concept that the Milky Way is a collection of stars, Heraclides' idea that the Earth rotates daily, or Aristarchus's idea, which Archimedes accepted, that the Earth rotates daily and orbits the Sun once a year. The Epicurean world. The beginnings of atomism. Philosophers who emphasized the many's plurality were opposed to Parmenides' focus on the one's unity. The idea of a void, in which countless separate entities moved, was opposed to the concept of a changeless, undifferentiated continuum. Anaxagoras showed this idea in the 6th century BC. They said the universe was infinite in extent and contained an endless number of small seeds. These seeds, later called atoms, indivisible, had properties that affected our senses, allowing us to see the world of matter. A universal rational mind, not God's, ruled the universe, and the same substances made up the heavens and the earth. Anaxagoras was accused of impiety and put on trial for heresy. He had powerful friends who defended him, and although he was acquitted, he fled the hostility of Athens. Leucippus of Miletus, who lived in the 5th century BC and is not well known, is credited with developing the atomic theory. He was the first to say that all events are the effects of previous causes. Everything happens out of reason and necessity. Democritus of Abdera, a student of Leucippus, said, "Nothing can be created out of nothing, nor can it be destroyed and return to nothing." The Athenian philosophers Socrates, Plato, and Aristotle did not accept Leucippus's atomist theory, as elaborated by Democritus. We are indebted to the later teachings of the Epicureans for keeping the atomists' ideas alive. The original atomist universe consisted of only atoms and space. There were an infinite number of atoms, and the space was also endless. Atoms were composed of the same material, but they had different shapes and sizes. They moved freely through the space, crashing into each other and coming together to form moons, planets, and stars, which slowly broke down into their atoms. Epicurus. Epicurus, 341 to 270 BC, from Samos, moved to Athens and founded the Epicurean school of philosophy, which was the first to admit women to its ranks. The Epicureans believed in the atomist theory, which posits that there is an infinite number of worlds composed of atoms. They also believed that humans are evolved and superior animals, that the gods are within us and not in the outside world, and that the best pleasures come from living in moderation and supporting one another. Their philosophy, based on atomist ideas, was very popular for 600 years in the Greco-Roman world among thoughtful people. Still, it died out when Judaism, Christianity, and Islam spread. Lucretius, a Roman poet, wrote The Nature of the Universe in the 1st century BC. In it, he praised Epicureanism and said, "Bear this well in mind. Nature is free and not controlled by proud masters. It runs the universe without the help of gods. Who can say for sure what the total sum of the measureless is? Who can hold the strong reins of the unfathomable in hands that are coercive? Who can make all the heavens spin the same way and set the fruitful earth on fire with the fires of ether? Who can be everywhere at once?" The answer was only nature itself. Religious groups attempted to limit the spread of Epicureanism as much as possible, making the gods even more powerful and distant. A surviving manuscript of the Lucretian poem was found in 1417 in an Eastern European monastery, and soon became widely known thanks to the invention of printing. Its effect, which historians have not documented much, may have been greater than Copernicus's work. The Stoic world. Zeno of Citium. Zeno of Citium, who lived from about 334 to 262 BC, started the Stoic school of philosophy in Athens. He taught in a roofed colonnade called a stoa, and his philosophy, known as Stoicism, appealed to people of all classes, from enslaved people to aristocrats. He praised the moral values of duty and justice. We can picture him saying to people walking by, "Have fortitude in the face of adversity, for fate rules the world. Don't cry. You're strong. The gods live in high places, in nature and us. The divine spirit beats on earth and in the heavens, getting stronger and weaker with each cycle on the wheel of time. Look at it all, but don't be amazed, because the soul has seen it all before." Edward Harrison, Darkness at Night. The writings of Seneca and Marcus Aurelius demonstrate how Stoic moral values and principles of behavior have permeated Western culture. In the 1st century BC, Stoicism was much more popular than Epicureanism, especially among the Romans. The Stoics believed that everything was predetermined by fate, which was revealed through divine spirits in both gods and mortals. They also thought that the mind ruled the universe. They believed that the stars were alive and that the universe was a living, breathing thing. The earth was also a living thing. The Stoics believed that the starry cosmos was finite and that a mysterious void existed beyond it. Some Stoic schools thought that the universe expanded and contracted over time, undergoing periodic massive changes. The Stoic universe, which was a finite, starry cosmos in an infinite void, served as the basis for the Victorian universe of the 1800s. The religions of mystery. The Mediterranean was where science, which studies and sorts things, started in the 6th century BC. At the same time, people in many other places were becoming more intellectual. The ideas of Zoroaster, or Zarathustra, in Persia, Iran, Gautama the Buddha and Mahavira the Jain in India, and Confucius and Lao Tzu in China, led to the rise of ethical religious movements. Moral codes of civil behavior were created based on spiritual teachings, even though they had nothing to do with religion before. The spread of these new ideas led to a decline in human sacrifice, a practice that had been prevalent in many religions before this. Zoroaster was the first prophet in Persia to teach that people would be rewarded or punished in the afterlife. The Medes and Persians accepted his belief in one God, Ahura Mazda, who rules the universe with light. They also believed that good people go to heaven and bad people go to hell. These ideas influenced the later religions of Mithraism and Manichaeism. The universe of the Middle Ages. Greek science reached its peak from the 6th century BC to the 2nd century AD, with notable contributions from Thales of Miletus to Ptolemy of Alexandria. By the end of the 2nd century AD, though, the fire of Greek inspiration had died down to a faint glow. The First Middle Ages. When the Roman Empire fell in the 5th century, Europe entered a cultural dark age, and intellectual activities ceased under the rule of barbarian invaders. During the Dark Ages, which were part of the early Middle Ages, the universe was perceived as a mythic split between heaven and hell, with the earth as a rectangular tabernacle surrounded by an ocean of water. Some scholars, such as Boethius and the Venerable Bede, were familiar with Greek learning through the Latin writings of Cicero, Pliny, and others. Even though European learning was in decline, Byzantium, Syria, and Persia were able to preserve some of the old knowledge. The growth of Islam. The Arabs left their deserts in the 7th century and built a massive Islamic empire that stretched from the Atlantic Ocean to India. The arts, crafts, and sciences thrived once more. Old forgotten manuscripts were gathered in libraries, and scholars migrated to Damascus, Baghdad, Cordoba, and other centers of the new civilization. Greek, Egyptian, Persian, Chinese, and Indian literature were translated into Syriac and then into Arabic, and these translations were compiled into lengthy commentaries. The new knowledge spread all over the world, even to Europe and China. By the 9th century, Islamic scholars had confirmed that the earth is round and that the universe is centered on the earth. We owe a great deal to the Islamic Empire, for preserving and sharing ancient knowledge that awakened Europe. Sadly, the Mongolian and Turkic invasions in the 1400s destroyed the old Islamic and Chinese cultures. The High Middle Ages. The early Middle Ages were dark, but exciting knowledge from Arab lands began to break through. New ideas, such as the concept that you need to understand, changed how people thought. In the 11th century, Anselm, the Archbishop of Canterbury, introduced the Empyrean, a sphere of purest fire where God was believed to reside beyond the stars. Many hard-working scholars translated the works of ancient philosophers, mathematicians, and scientists, such as Plato, Aristotle, Euclid, and Galen, into medieval Latin. They did this first from Arabic, and then directly from Greek. The new knowledge went beyond what the monastery and cathedral schools could teach, so groups of translators and learnt scholars started the universities. Thomas Aquinas demonstrated in the early 1300s how to reconcile Christian beliefs with the Aristotelian universe through a few minor adjustments. People stayed immortal, but the universe lost its eternal nature. The 14th century was the height of the medieval universe. It was a grand unification of the physical and spiritual worlds, blessed by religion, approved by philosophy, and explained by geocentric science. However, in the 13th century, when Europe was awakening again, people were already pleased with Aristotle's physics and Ptolemy's astronomy. Roger Bacon, a Franciscan monk, stated that the scientific method is based on making observations, not relying on old texts, using mathematics, and testing calculations through experiments. Christian doctrine was in danger when everyone started using Aristotelian learning, and church leaders were worried. They agreed that the Earth is a sphere at the center of the universe, but they disagreed with Aristotle's argument that God couldn't move the Earth or create other worlds if he wanted to. In 1277, Étienne Tempier, the Bishop of Paris, announced the 219 condemnations, which went against the Aristotelian limits on God's power. The bishop said that God's power knows no bounds, and that God, who is limitless, is everywhere, and cannot be limited to one place. The condemnations constitute a significant event in the history of cosmology. The idea of an all-powerful God blew up the limits of the Aristotelian universe. The universe had to be able to hold an infinite God. Thomas Bradwardine, who became Archbishop of Canterbury, said, "God is that whose power is not numbered and whose being is not enclosed." This was similar to what Empedocles wrote in the 5th century BC. God is an infinite sphere whose center is everywhere and its circumference nowhere. To this end, Bradwardine turned Anselm's Empyrean into an infinite extramundane void. There was a mysterious, endless place beyond the stars where God lived. He changed the limited Aristotelian universe into an unlimited Stoic universe. In the 14th century, Nicolas Oresme, who lived in France, said, "Motion can be perceived only when one body alters its position relative to another." He refuted old arguments that the Earth could not rotate, and pointed out that Heraclides' theory of a rotating Earth greatly simplified the structure of the heavens. The poem The Nature of the Universe was discovered, and it changed the minds of many people in the 15th century. It introduced them to the exciting idea of an infinite universe. Cardinal Nicholas of Cusa said that since God made the universe, which has no edges or center, it must also have no edges or center. He wrote the famous line, "The universe is a sphere of which the center is everywhere and the circumference nowhere," in his book Of Learnt Ignorance. This means that the creative universe had the same properties as the creator. Nicholas of Cusa said that it is easy to think of the Earth as the center of the universe, but there is no reason to do so. There is no real center, and he couldn't see why the Earth shouldn't move. The universe is heliocentric. The Pythagoreans initiated the Copernican revolution, while the Cartesians and Newtonians ultimately concluded it. Aristarchus and Copernicus were its heroes. The revolution happened. The revolution freed them from their obsession with the Earth and made it possible for the anthropocentric universe to be overthrown once and for all. Copernicus. Nicholas Copernicus, 1473 to 1543, a Catholic Church canon, showed in the 16th century that a heliocentric universe was possible. He studied the Ptolemaic system while he was a student in Italy and was disappointed that it didn't follow the Platonic ideal of perfect circular motion. Aristotle agreed with this idea, but Ptolemy changed his mind when he developed the concept of equants. Copernicus was also aware of Aristarchus's idea that the Sun is at the center of the universe. This theory states that the Earth orbits the Sun, which causes the other planets to appear to move back and forth across the sky. Copernicus thought that a heliocentric system could get rid of equants and bring back the idea of perfect circular motion. He spent his whole life building and calculating heliocentric orbits. Revolutions of the Celestial Spheres, Copernicus's huge work, that is as big as the Almagest, came out in 1543, not long before he died. In an earlier work, he wrote, "All orbs revolve around the Sun, taken as their center point. Therefore, the Sun is the center of the universe." In the Revolutions of the Celestial Spheres, he wrote, "Why then do we hesitate to allow the Earth the natural mobility of its spherical shape, instead of proposing that the whole universe, whose boundaries are unknown and unknowable, is in rotation?" The arguments he used to justify the Earth's rotation were similar to those proposed in the previous century by Oresme. It was easy to go from a rotating Earth to a moving Earth. We, therefore, assert that the center of the Earth, carrying the Moon's orbit, passes in a great orbit among the other planets in an annual revolution around the Sun, that near the Sun is the center of the universe, and that whereas the Sun is at rest, any apparent motion of the Sun can be better explained by the motion of the Earth. Oh no! Most astronomers didn't believe it at first because the Copernican dream of a simpler universe didn't come true. The more Copernicus worked to make the heliocentric system fit with what he saw, the more circles he needed. He needed more circles than ever before because he had to give up the use of equants. But he still couldn't match Ptolemy's level of accuracy. The universe is infinite. Thomas Diggers. Thomas Diggers, an astronomer and mathematician, was born in 1543, the same year that Copernicus died. In A Perfect Description of the Celestial Orbs, published in 1576, he provided a more detailed discussion of the Copernican system. He made a significant change by spreading the sphere of stars out over all of space. Diggers wrote, "This orb of stars, fixed infinitely up, extends itself vertically." The universe had its sphere of stars ripped apart only 33 years after the publication of the Revolutions of the Celestial Spheres, and exactly 200 years before the Industrial Revolution and the American Declaration of Independence. The Perfect Description underwent numerous editions in the late 16th century, which led to ideas that altered the material world. Bruno Giordano. When Diggers's book became popular, Giordano Bruno, a monk, lived in London. He was very excited about the idea of an edgeless universe and stressed the logical conclusion, which Nicholas of Cusa and others had already made, that the universe must also be centerless. In the universe, there is no center and circumference, but the center is everywhere, he wrote. Bruno spread a Christianized version of the Epicurean universe from Lucretius's poem through his writing and travels. This universe is infinite in size and contains many planetary systems teeming with life. Thus is the excellence of God magnified, and the greatness of his kingdom made manifest. He is glorified, not in one, but in countless suns, not in a single earth, but in 1,000, I say, in an infinity of worlds. Bruno was the revolutionary champion of the Copernican revolution. He spent the last 7 years of his life in an ecclesiastical prison, where he was tortured and tormented. He refused to recant and was burned at the stake in Rome in 1600. Tycho Brahe. Before telescopes were invented, Danish nobleman Tycho Brahe, 1546 to 1601, studied the planets with the highest level of accuracy possible. He didn't like the Copernican system for a simple reason. He said that if the Earth made a vast circle around the Sun once a year, the stars would appear to be in different places at different times of the year. His observations didn't detect this change in angle, parallax. Should we send the stars so far away that we can no longer measure parallax? He said that the stars, as we can see them with our own eyes, have a specific size and are not just points of light with no size. If parallax couldn't be seen, stars would have to be much bigger than the Sun to look the way they do. We now know that the apparent size of stars, which is caused by diffraction, is misleading, and that stars are even farther away than Tycho thought. Johannes Kepler, 1571 to 1630, was a creative scientist who overcame his poor health and became the Holy Roman Empire's imperial mathematician. Voltaire called it an agglomeration that was called and still calls itself the Holy Roman Empire, but was neither holy nor Roman, nor an empire in any way. He agreed with the Copernican system, which had the Sun at its center and a sphere of fixed stars at its outer edge. He was opposed to the extreme idea of an infinite universe with no center. He was horrified by the idea of an endless universe. In 1606, he wrote, "This very thought carries with it, I don't know what secret, hidden horror. Indeed, one finds oneself wandering in this immense city, to which are denied limits and centers, as well as all determinate places." Kepler's first book, Cosmographical Mysteries, was published in 1596 and was an attempt to find out the truth about the cosmos. This work contained numerous ideas that would later inform Kepler's research. The last imperial mathematician was Tycho Brahe. Kepler obtained Tycho's careful and detailed notes about the planets, and for years he attempted to determine how they moved, especially Mars. He finally won and freed astronomy from the idea of epicyclic motion. The three main laws of elliptical planetary motion that he came up with were the building blocks of the Newtonian world system. Galileo. Galileo Galilei was born in 1564, the same year as Shakespeare, and died in 1642, the year Newton was born. The telescope played a crucial role in his astronomical work. What Galileo saw through his telescope didn't match what Ptolemy taught. His ideas contradicted the Aristotelian view that spirits reside in the sky. He stated directly that the sublunar and celestial realms are physically the same. When you look closely and think critically, you can see that the Earth rotates around an axis every day and around the Sun every year. Galileo agreed with the Copernican system, but was not interested in Kepler's ideas. In 1610, he published The Starry Messenger, which included his discoveries about the Moon's mountains, Jupiter's moons, and many other stars in the Milky Way that had not yet been explained. He talked about Tycho's criticism of the Copernican system. Galileo's telescope made objects appear 30 times larger, but stars still seemed the same size as they did with the naked eye. He was right that their size was misleading. The people who hated Galileo the most were scholars and priests who were well versed in Aristotle's work. He compared the geocentric and heliocentric systems in the two great systems of the world and made fun of Aristotle's physics and Ptolemy's astronomy. His beliefs caused problems with church leaders in his old age, and when they threatened to torture him, he changed his mind and rejected the heliocentric system. The harmonic mean was significant in music and math. Keep in mind that the 8 corners of a cube are the harmonic mean of its 6 faces and 12 edges. The Pythagoreans proved the geometric algebraic rule that the square of the diagonal length of a right triangle equals the sum of the squares of its sides. The Babylonians had already found this rule. So 3, 4, 5 and 5, 12, 13 are the sides and diagonals of 2 right triangles. Pythagoreans found that integral or fractional numbers can't show the sides and diagonal because they are usually incommensurable. 2 Zeno of Elea, a Greek philosopher from the 5th century BC who lived in southern Italy, said that the senses can't find the truth. The real world is unchanging and eternal. The world we see is fake and temporary. He's best known for his paradoxes, which attempt to demonstrate that the change we perceive is not possible. The paradoxes are similar. The race between Achilles and the tortoise is the most well-known. Let's say the tortoise starts 100 meters ahead of Achilles, who runs 100 times faster than the tortoise. The tortoise moves 1 meter for every 100 meters that Achilles runs. For every 1 meter that Achilles runs, the tortoise moves 1 centimeter, and so on, in an infinite number of smaller steps. Achilles gets closer and closer to the tortoise, but he never passes it. The paradox is wrong, because the endless number of steps only takes up a finite amount of time, and the senses show that Achilles passes the tortoise. Philosophers, on the other hand, are still arguing about the paradox. The question is whether space and time are both real and can be divided into smaller parts. But countless atoms, moving in countless ways through endless time by colliding with each other and their weight, have come together in every way possible and realized everything their combinations could make. So it happens that a journey of incredible length, during which they have experienced every kind of movement and connection, has finally brought together those whose sudden encounter normally starts the formation of substantial fabrics, earth and sea and sky, and the races of living creatures. Lucretius, The Nature of the Universe. 4. Plato made universal ideas like truth, beauty, justice, and perfection divine, which gave shape to the chaotic world of matter. Aristotle made these ideas secular and connected them to material things in a way that couldn't be separated. In mythology, the gods were in charge. In Plato's world, the mind was in charge. In Aristotle's world, the forms were in charge. Aristotle brought back the spirits of the time of magic, but differently. The spirits were now the hidden forces and natural properties of matter. They had turned into the souls of things, and they still exist as forces, masses, momenta, energies, potentials, wave functions, and so on. People still live in a world of magic, but now the fickle spirits are the disciplined dancers in a ballet of weaving waves and forces. 5. The Jews who were exiled to Babylon in the 6th century BC saw how Zoroastrianism divided good and evil. They altered many of their moral ideals to align with their type of monotheism. Zoroastrianism influenced the wisdom literature of the Jews. For example, in the books of Job, "Where were you when I laid the foundations of the earth?" Psalms, "Yea, though I walk through the valley of the shadow of death, I will fear no evil, for you are with me, your rod, and they comfort me." And the Song of Solomon, "Who is she that looks forth as the morning, fair as the moon, clear as the sun, and terrible as an army with banners?" Zoroastrian idealism, with its hereditary mix of angels and demons, has had a significant impact on Judaism, Christianity, and Islam. From the fall of Babylon in the early 5th century BC to the time of St. Augustine of Hippo in the late 4th and early 5th centuries, the Mediterranean world was exposed to Zoroastrianism through its derivative religions of Mithraism and Manichaeism, and by its infiltration of Greek philosophy, Jewish prophetic literature, and Gnostic and Neoplatonic theologies. 6. Human tides have washed across the globe, crushing nations and carving out empires, led by God-inspired men who sought to write their will across the sky and stars. One such leader was Alexander the Great, who crossed the Hellespont in the 4th century BC, subjugated Asia Minor and Egypt, vanquished the armies of the Persian Empire with his cohorts, quelled the turbulent forces of Afghanistan, crossed the Hindu Kush, and invaded and defeated the nations of the Punjab. Eastward flowed Hellenic science and philosophy in the wake of Alexander's conquests. Westward flowed Oriental philosophy and religion. Westward into the Mediterranean world came the Zoroastrian Lord of Light, the glorious Ahura Mazda, embattled with the Lord of Darkness, bringing the belief that the soul is divine and that worshipping gods apart from the appointed one is a sin. Westward into the Roman legions came the religion of the dying and resurrected martyred god, the triumphant Mithra, bringing the sacramental eating of the flesh of God and the notion that evil is the privation of good. Westward came the Babylonian story of creation and the flood, the Persian stories of heaven and hell, the last day of judgment, and the resurrection of the dead. All these stories reshaped the theology of the Greco-Roman world, paving the way for the rise of Christianity. Edward Harrison, Masks of the Universe. And we must not forget that westward came ethically inspiring cults, such as the cult of the Divine Mother, Isis, holding her child. 7. Following the growth of ideas during the long Middle Ages takes the historian into a maze of confusing beliefs. The medical knowledge and alchemy learned from the works of Jabir ibn Hayyan, a court physician to Harun al-Rashid, the Caliph of Baghdad, famous for the 1001 Nights, became widely known. Jabir was later Latinized into Geber, and because of the rigmarole and obfuscation of the numerous works attributed to him, the word Geberish eventually became gibberish. Edward Harrison, Masks of the Universe. The same principles apply to the macrocosm, the universe, and the microcosm, the individual, in alchemy and astrology. This was the great analogy. The chemical elements and the parts of the human body corresponded with the planets and other heavenly bodies. Silver was associated with the moon, quicksilver with Mercury, copper with Venus, gold with the Sun, iron with Mars, tin with Jupiter, and lead with Saturn. Roger Bacon, 1220 to 1292, had a prophetic vision of the invention of telescopes, submarines, steamships, cars, and flying machines. He wrote, "Machines for navigation can be made without rowers, so that the largest ships on rivers or seas will be moved by a single man, in charge with greater velocity than if they were full of men. It is also possible to design cars that can travel at very high speeds, even in areas with no animals present. Furthermore, flying machines can be constructed so that a man sits amid the machine, revolving some engine by which artificial wings are made to beat the air, like a flying bird." Europe was in the midst of a technological revolution, marked by the introduction of stirrups, heavy plows, water mills, windmills, textile mills, magnetic compasses, gunpowder, pattern-welded steel, and the development of paper-making. Bacon's extrapolations were not so fanciful, given the contemporary technological developments that occurred 5 centuries before the Industrial Revolution. It has not consistently been recognized that the technology revolution occurred not in the 18th, 19th, or 20th centuries, but in the high Middle Ages of the 13th century. Many developments, stirrup, watermill, windmill, gunpowder, papermaking, and magnetic compass, came from outside Europe. But Europeans were the first to apply them widely and make technology a fundamental part of society. See Science in the Middle Ages, David Lindbergh, editor. William of Ockham, about 1280 to 1349, an Oxford scholar at Merton College, opposed the Platonic philosophy that ideas are the actual reality. He said ideas are often empty names, and the actual realities are the objects themselves. His viewpoint has been summarized with the words, "Entities must not be needlessly multiplied." People often interpret this principle, known as Occam's razor, as the preferred theory with the fewest and simplest assumptions or ideas. Occam used this argument to criticize Aquinas's theological elaborations of the Aristotelian universe. Occam's razor is helpful in cosmology when comparing rival universes. The preferred universe explains the observed world using the fewest and simplest ideas when all other factors remain equal. In the early 14th century, Dante Alighieri, a political refugee from Florence, wrote the epic poem The Comedy. The word divine was added to the title in the 16th century. In this imaginative poem, he placed the angelic spheres of the old Gnostic and Neoplatonic cosmologies in the Empyrean, arranged in such a way that the realm of heavenly spheres and celestial spheres mirrored each other. In his unified model, God became the center of a theocentric realm. The earth remained the center of a geocentric realm, and God and earth were the antipodes of each other. Dante's exceptional amalgamation of the material and spiritual realms emerged later and never gained widespread acceptance in the mainstream of cosmology. Only a few decades previously, in 1277, the notion of God confined to a fixed place in space had been condemned as contrary to orthodox doctrine. In Two Great Systems of the World, Galileo defended the Copernican system in a made-up debate with an imaginary Aristotelian named Simplicius. Alfred Whitehead, Science and the Modern World, says Galileo keeps talking about how things happen, while his opponents had a full theory about why things happen. Unfortunately, the two theories did not yield the same results. Galileo talks about irreducible and stubborn facts, while Simplicius, his opponent, gives reasons that are entirely satisfactory to him. Considering this historical uprising as an appeal to reason is a significant mistake. It was an anti-intellectual movement. It was a return to considering simple facts, which was a reaction against the strict logic of medieval thought. I am only repeating what the supporters of the old regime said at the time when I say this.